What did Earth look like before the first breath of life, before the slow chemical murmurs that would one day become memory and song? The question itself is a small, stubborn light in the dark, a single filament of curiosity stretched across 4.5 billion years. It demands a different kind of imagination, not the imagination of people or cities or forests, but of planetary processes writ in heat and stone, of silence deeper than any human silence. I'd ask the listener to stand for a moment on the lip of time and peer back into the Hadean, the era between 4, 6, and 4.0 billion years ago, when the planet was young in the most violent, incandescent sense. The Hadean was not merely ancient, it was formative in ways that still hummed the deep frequencies of the world. It began in the smoky aftermath of the solar system's birth. Gas and dust, stirred by gravity and lightning thin currents, had coalesced into planetesimals. These clumped and collided, each collision a small apocalypse. The newborn Earth, still assembling, was a place of mosaic chaos, rock, metal, and molten matter consolidating under ceaseless impacts. The imagination that seeks this past must imagine a scene where geometry is crude and colossal forces are ordinary, accretion, differentiation, and the forging of a core that would, in time, generate a magnetic field to cradle life. The most vivid emblem of that tumult is a collision whose echoes shape what is known today as the Moon. A body roughly the size of Mars, later named Theia, intersected with proto-Earth in a cataclysmic event. The violence of that meeting cannot be overstated, a planetary-scale blow, an eruption of molten material and vapor that racked the young planet in a blistering plasma. From that storm of debris rose a companion, the Moon, and with it a new pattern of tides and rotational rhythm. The Earth left that collision warmer, more fluid at its outer layers, sculpted by a hand that would keep striking for tens of millions of years to come. To visualize the Hadean is to trade the palettes of green and blue for one of orange and white hot metal. Vast oceans of magma likely swirled across the surface, pockets of incandescent stone churning like planetary potter's clay. It was a time in which surface and interior were in exchange. Heavy metals sank, lighter silicates rose, and the differentiation of core and mantle was an ongoing conversation of gravity and heat. The atmosphere was thick, not with oxygen but with steam, carbon dioxide, methane, ammonia, and sulfurous gases, a greenhouse of chemical fire. Above, the sky could have been a bruise of incandescent clouds, lightning digging white scars across steam and ash. Everywhere impact rained down. Some arrivals were small, brief flares, others were epochal. The bombardment delivered heat, pulverized crusts, and seeded the planet with exotic materials brought from the far reaches of the bedlam that was the early solar system. Each impact reset parts of the landscape, erasing nascent features and washing the surface in fresh thermal and mechanical energy. The record of those collisions remains incomplete. Much was overwritten, vaporized, or mixed away. The Hadean left only fragments of itself, some trapped in crystals that survived the centuries, zircons older than 4 billion years that whisper of cool patches, fleeting oceans, and a crust that had begun to stabilize. Those zircons are relics and reminders. Their very existence complicates the stereotype of an endless inferno. Within these tiny time capsules, geologists have found evidence that pockets of the crust may have cooled, that water, liquid, placid, oceanic water, existed earlier than once thought. It suggests that the Hadean was not a monolithic furnace, but a mosaic of extremes, molten expanses alongside nascent, perhaps ephemeral seas. The interplay of heat and water would, in time, be crucial. Where magma met water, there was chemistry as violent as it was creative, hot vents exhaling mineral-laden plumes, reactions that reconstituted molecules into new forms, and elemental gradients that could, in a different time, have become the crucibles of life. Close attention to the Hadean must also take account of atmosphere and magmatism. The formation of the metallic core was not only a structural event, it was also the start of a planetary heartbeat. As molten iron sank and convected in the core, it generated magnetic fields that could shield incipient surfaces from the full brunt of solar wind. Without that tentative protection, light atoms could be stripped, and a fragile atmosphere would be eroded. The nascent magnetosphere was, therefore, an early act of preservation, a stagehand keeping the fragile set intact until biochemistry learned its first lines. But to think of the Hadean only in terms of chemistry and magnetism is to miss the theater of experience. The scene was loud and the language of elemental motion. Storms were not the polite periodic affairs of later eras. They were titans of vapor and fire. Rivers of lava carved new topography, gliding across uneven ground, swallowing older stone in a slow, insistent flow. Volcanoes were arterial, belching plumes thick with ash and with gases that painted the sky in tones no modern eye has seen. Rain, when it fell, was not life-giving in the way later rains would be. Acid and heat could render it corrosive, scouring nascent surfaces and altering the chemistry of any pools it reached. There is a particular kind of terror and tenderness in imagining that world. Terror because the forces at play are impersonal and immense. Tenderness because, beneath that terrible theater, the stage was being set for everything that followed. The textures of the planet, its first stable crusts, its early basins, its chemical soup, were shaped by chance and necessity, by impact and cooling, by the slow negotiation of pressure and chemistry. It is a sobering thought that much of what was made was also unmade. The Hadean is less a continuous narrative than a collage of fleeting chapters, an ocean here, a dried basin there, a transient atmosphere, a brief stabilization, all subject to erasure by the next bolide. It is tempting to ask a speculative question here. Could there have been anything recognizably persistent in the Hadean? Anything that might resemble habitability as later eras would know it? The evidence suggests possible answers without certainty. Temporary surface water seems plausible in pockets and perhaps in globalized oceans after the planet cooled enough to condense steam. Short-lived continental crust may have formed, was disrupted, and reformed. Under these fitful conditions, the chemistry of life, amino acids, simple peptides, building blocks of more complex molecules, might have been synthesized and destroyed in cycles, like a draft of music that never quite reaches a chorus. That image of chemistry rehearsing the possibility of life without ever debuting it fully is the most haunting thing about the Hadean. It lays down the paradox of origins, that creation requires destruction, that stability is born of cycles of disturbance, and that the seeds of life might have been planted an infinite number of times only to be plucked before maturity. The Hadean, therefore, reads as both opportunity and erasure. It is the era that could generate the first organic experiments and then obliterate them with its next tantrum. As the world cooled and the frequency of impacts diminished, the Hadean gave way to calmer regimes without ever losing the memory of violence. Yet the memory is not only in scarred rocks, it is encoded in the dynamics of the planet itself. The tilt, the length of a day, the chemistry of oceans, all filtered through that fierce childhood. Time, which in human life is measured in moments and years, stretches into a different currency here. Hundreds of millions of years to ferment a crust, tens of millions to sculpt the stable basin, and a lifetime of collisions to alter trajectories permanently. The listener must grasp the scale not as abstraction, but as a kind of patience the planet possessed and people lack. A patience that permitted repetitive destruction and slow accretion until, finally, the conditions for something new could be sustained. Another way to feel the Hadean is to consider the absence that defines it as much as its presence. There was no oxygen-rich air, no green photosynthetic carpets, no limbs or eyes to witness the sky. Silence, in the modern sense, did not exist. Instead, there was the constant mechanical music of a planet in flux, rumbling magma, the percussion of impacts, the whisper of vapor-laden winds. It was a soundscape suited to geological ears, not biological ones. Yet this absence is itself a kind of presence. The conditions that exclude life also provide a canvas upon which life, once it appears, can rapidly contrast itself. Humanity tends to measure the worth of a place by the life present there. The Hadean offers a contrary lesson. The planet's earliest worth was its potential, a raw physical potential that would, given time and quiescence, transform into something else entirely. There is also a moral tone to this opening chapter. Not a moral in the human sense, but a lesson in humility, that beginnings are not tidy, that foundations are often rough, and that the survival of a future depends on a long negotiation between catastrophic events and incremental recovery. The Hadean is at once ugly and magnificently forgiving. It breaks things, and then, in its own slow way, fashions new possibilities from the broken pieces. There is comfort in that, especially for a listener who lives in an age of rapid change and frequent upheaval. The planet itself has a history of resilience and reinvention, writ in basalt and zircon. If the Hadean were a person, it would be a youth of raw charisma and poor manners, brilliant, reckless, and spectacularly destructive. But it is not a person, and here the analogy must end. The reality is soberer and more profound. The Hadean is the first long chapter of a story that does not yet know its characters. It is a preface in which the grammar and vocabulary of a future narrative, life, climate, continents, atmosphere, are assembled. Many drafts of that narrative were discarded, some lines were erased and rewritten. What survived into the later epochs did so because conditions changed from violent to permissive, because energy gradients moderated, and because chaos loosened its grip just enough to allow persistence. At the close of this opening reflection, the Hadean insists on its own mystery. Evidence is fragmentary, inference is risky. The record is partial because the era itself is a master of erasure. Yet within the fog of lost particulars, a pattern emerges, that the planet's early life, in the geological sense, was dominated by processes that alternately destroyed and created, and that from this alternation, in some improbable, patient way, the stage was set for the possibility of life. The astonishment is twofold. First, that anything familiar survives such an incandescent infancy, and second, that the narrative of Earth could pivot from heat and violence to the delicate economies of biology. The question with which this chapter began, what did Earth look like before the first breath, resists clean answers. But it does not resist wonder. To stand at the doorway of the Hadean is to confront the fundamental truth of beginnings. They are noisy, they are uncertain, and they are capable of producing outcomes that outlast the chaos that birthed them. This is not a comfortable thought, but it is a generous one. It promises that even in a world defined by immense mechanical cruelties, there is room for possibility. It promises, too, that the earliest eras of Earth's existence are not mere prehistory, they are active participants in the story. That will follow. The heavy-handed editors who rearrange the plot so that life could one day speak, so the narrative moves forward, deliberate and inquisitive. The Hadean closes not with a clean curtain, but with a lingering question and an invitation to look closer. How did matter, heated and smashed into new forms, find its way into patterns that could be sustained? How did fleeting oceans and volatile atmospheres become the persistent media of chemistry and, eventually, of biology? These are the questions that will carry the voice onward into the Archean and beyond. For now, however, the Hadean remains the prologue, fierce, formative, and full of unanswered possibility. It asks the listener to remember that beneath every quiet grove and every city street lies a history of fire and rain, a time when the planet was raw and the rules were still being written. In that remembering, the human present finds both its fragility and its inheritance. What does it mean for a world to be born out of nothing more than scattered grit and a stubborn law of attraction? That question sits like a tiny catalyst at the heart of the planet's earliest chapters, a thought experiment that asks the listener to imagine mass without form, motion without purpose, and then the slow, inexorable choreography by which chaos accretes into shape. The formation of Earth began as a whisper in a disk of gas and dust surrounding a very young sun. Those grains of silicate and metal drifted in a thin, cold plane, colliding gently at first, then more forcefully as gravity coaxed neighbors into partnership. The initial truth of planetary birth is simple and brutal. Growth is a conversation of collisions. Tiny particles found each other and stuck. Pebbles became cobbles, cobbles became boulders, and boulders, under the right conditions and with a little luck, became planetesimals. In that nursery, chance interactions were written into destiny. A slightly larger body had a marginally stronger pull, and that advantage, over thousands, then millions of years, allowed it to monopolize material in its orbit, in a process known to geophysicists as runaway accretion. To translate that language into images, imagine a slow flurry of snow in a wide, thin room. Each flake that lands slightly increases the height of the drifts that follow it. A bump, a slope, a shadow alters where the next flake will fall. The proto-Earth was like that drift made celestial, a growing hump of mass that began to dominate its neighborhood, sweeping up smaller debris in a gravity-fed harvest. But this harvest was not gentle. It was composed of high-velocity unions, of impacts that delivered not peace but dramatic bursts of heat and transformation. Those collisions were formative in two ways. Mechanically, they delivered angular momentum and mass, altering rotation rates and tilting axes, setting the rhythms by which a planet would later mark its days and seasons. Chemically, they were agents of mixing. Incoming bodies carried minerals, metals, and volatile compounds, water, carbon, nitrogen, sometimes locked in ices or bound within primitive minerals. Each arrival could be a depositor of ingredients for a future chemistry or an eraser of some nascent arrangement already in place. The pattern of early growth was not uniform. Some regions of the disk birthed a handful of larger embryos that jostled, merged, and occasionally cannibalized each other. The Earth that emerged was not a product of smooth accretion alone, but of chaotic selection. Every once in a while, an especially consequential meeting would occur, an event so energetic that it would reset the surface and the very identity of the planet. The most famous of these later was the collision that birthed the Moon, a reminder that the drama of formation is not merely additive, it is occasionally revolutionary. Beneath the geometry of collisions is a ledger of energy. Each accreted kilogram, arriving at orbital speeds of kilometers per second, imparted heat, sometimes enough to melt local crust, sometimes enough to liquefy large swaths of the young globe. The early Earth was therefore a landscape of thermal extremes. The notion of a cool, stable surface is anachronistic here. Instead, the dominant feature was a vast magma ocean, a convecting sea of molten rock that covered large tracts of the planet for perhaps millions of years. This ocean was a dynamic medium. Currents of silicate melt flowed, cooled, and reforged, carrying heat inward and outward in a planetary scale, boiling. That magma ocean was no static bath. It was being pried apart by sinking metal and rising silica, a process called differentiation. Heavy elements, iron, nickel, and other siderophiles, surrendered to gravity and plunged toward the center, their descent liberating latent heat and chemical differentiation. Lighter materials, enriched in silicon and oxygen, rose to form a primitive mantle and a progressively solidifying crust. Differentiation is an act of separation and definition. It turns a ragbag of ingredients into a layered body with a core capable of generating magnetic fields and a surface capable, eventually, of holding oceans. The descent of metal into a forming core had consequences that extended beyond geology into planetary atmosphere and habitability. As the core began to convect, it set the stage for the emergence of a magnetic field, not immediately, perhaps, and certainly not a field like the stable geomagnetic shield that protects life today, but a nascent dynamo nonetheless. That dynamo mattered because the young sun was a far more tempestuous neighbor than it is now. Its early wind and ultraviolet output were harsher, capable of stripping away light gases unless they were anchored by a larger atmospheric mass or sheltered by magnetic protection. In this way, core formation was not merely a structural development, it was a preliminary act of planetary preservation. As ions sank, volatiles moved elsewhere. Heat expelled gases trapped within minerals, melting and degassing set free water vapor, carbon dioxide, methane, ammonia, and sulfur dioxide into a thick, roiling atmosphere. This outgassing, coupled with late infall of icy bodies from the colder reaches of the disk, determined whether the planet would be wet or dry. The record preserved in mantle chemistry and in isotopic signatures hints that both internal degassing and external delivery were important contributors to Earth's initial volatile inventory. The balance between them, which was greater and when, is a matter of ongoing investigation, and in that uncertainty lies the mystery of habitability itself. Around this furnace of formation, a different kind of violence continued, impact after impact. The narrative must linger on these collisions because each one mattered differently depending on size, speed, composition, and timing. Small impacts are frequent and locally transformative, churning regolith and delivering tiny inventories of exotic minerals. Large impacts were infrequent but catastrophic, melting crustal volumes, blasting vapor into space, and in some cases, resetting the planetary calendar for millions of years. A single giant impact can vaporize oceans, strip atmospheres, and respawn surfaces. It can also seed the circumplanetary environment with debris dense enough to coalesce into a satellite. It is instructive to imagine an impact not as a moment, but as a compact narrative arc. There is a long, silent approach as a body slides through space, obedient to gravity's pull. Kinetic energy builds like a compressed spring. Then, in the blink of geological time, the collision occurs. Shock waves race through rock at tens of kilometers per second. Temperatures spike to thousands of degrees, and matter is vaporized, melted, or flung outward in a gigantic plume. The sky fills with incandescent ejecta. A ring of molten glass may bead into spirals and fall back as a rain of anger across the planet's surface. Where the impactor strikes, the crust is rearranged into basins, terraces, and high walls. If the impact is truly massive, it throws material into orbit, and the geometry of that debris can, under the right circumstances, become the seed of a moon. The moon-forming collision, a topic already sketched in the previous chapter, stands as a paradigmatic example. Theorists imagine a Mars-sized Theia colliding with proto-Earth at a glancing angle, a meeting so energetic that a substantial fraction of material was vaporized and placed into orbit. Out of that debris disk, gravitational instabilities coalesced, producing a satellite that would, in time, stabilize tides and modulate rotational dynamics on the young planet. The moon's creation was both an act of violent subtraction and creative addition. It robbed Earth of angular momentum and mass, yet it established new rhythms, longer days, tidal mixing of oceans, and a stabilizing influence on Earth's obliquity that may have been crucial for long-term climate moderation. And yet, collisions did not simply sculpt physical structure, they sculpted possibility. Each impact had the capacity to sterilize surfaces, but also to mix and distribute materials that could later participate in prebiotic chemistry. Heavy bombardment could bury pockets of chemistry deep into the crust, preserving them from surface calamities. Impacts could excavate mantle materials, exposing new chemistries to the surface environment. They could deliver organics, or they could remove volatiles by blasting them to space. The same act could end the local experiment and begin another. In this sense, planetary formation is a pedagogy of risk, trial and error written rock and fire. Within the molten folds of early Earth, there were pinpricks of permanence. Crystals that grew in slowly cooling melt pockets, notably zircon grains, survived eons of reworking and preserve isotopic. Tales of temperature, liquid water presence, and crustal processes within their lattice structures. These microarchives show that not everything was continually annihilated. Here and there amid the heat, the planet allowed itself cool canvases, nascent crusts, ephemeral seas, and pockets of hydrothermal systems that could, for fleeting epochs, maintain chemical gradients. It is the scale of these pockets, small, fragile, brief, that both humbles and fascinates. Against the sweep of bombardment, they are like contraband stability, improbable, precious, and fleeting. The atmosphere of the young planet was equally provisional. A steam-saturated sky condensed as the planet cooled, and the first rains were more like a barrage than a gentle replenishment. The chemistry of early precipitation could be corrosive, laden with dissolved gases and metals. But where rain met heat, chemical reactors were born. Lava sea margins, places where molten rock met condensate vapors, would have been crucibles. Complex mineral chemistries precipitated there, and mineral surfaces catalyzed reactions that, in quieter times, might have assembled increasingly complex organic molecules. Hydrothermal vents, both on the seafloor and in groundwater, set up gradients of temperature, pH, and redox potential that are now considered fertile grounds for the chemistry that precedes biology. Time must be kept in a different key to feel the significance of these early scenes. What seems forever to humans, a decade, a millennium, is barely a page-turn in planetary history. The magma ocean might last millions of years. A giant impact can alter climate for tens of millions more. Yet those intervals are finite and, crucially, they allow for cumulative effects. Repeated cycles of melting and cooling, of impact-induced resetting and incremental stabilization, create opportunities for systems to move from novelty to persistence. It is this patience, this geological stubbornness, that transforms a chaotic young world into a cradle capable of sustaining more complex chemistries. There is a moral texture to the way collisions and accretion operate. They are indifferent, but consequential. The processes that made Earth did not intend life. They merely followed physics. Yet from indifferent mechanics came structures and environments that would later be co-opted by life. The listener is asked to accept a paradox. The same forces that threaten the possibility of life are also those that supply its materials and shape its habitats. In that paradox lies a deep consolation. Creation and destruction are not opposites, but partners in a long, patient dance. The narrative of planetary formation finishes this section not with finality, but with an accumulation of consequences. The Earth that emerged from those incandescent centuries was layered, magnetized, and volatile rich. Its spin and tilt bore the imprints of early impacts. Its crust, while incomplete and frequently reworked, began to present niches where chemistry could persist longer than before. Water, whether delivered externally or outgassed internally, began to collect, condense, and circulate. Most importantly, the stage had been set for the next act, a quieter chapter where chemical complexity had a chance to deepen unmolested by the worst of the bombardment. That quieter time would, in the geological timeline, still be vast, long enough for improbable events to become inevitable. To end this chapter is to linger on the feeling it bequeaths, a sense of smallness before scale, an appreciation that what feels essential now, ocean's stable crust, a protective magnetic field, were once precarious and provisional outcomes of a violent adolescence. The formation of the planet was not a single miracle, but a sequence of many collisions that sometimes destroyed and sometimes created. differentiations that organized interiors into layered order, and the slow accretion of volatiles that would one day play host to metabolism and memory. The listener can imagine this, not as a tidy checklist, but as a living, abrasive process that wrote deep rules into the Earth's bones. Those rules would govern everything to follow, whispering through rock and water, shaping climates and chemistries until, in the slow turn of epochs, the first hints of life would learn to read them. What does it take to rearrange the destinies of two worlds in a single collision? How much energy must be poured into a single instant for a quiet, dark companion to be birthed and for a planet's axis and seasons to be rewritten? These are not merely geological curiosities, they are the kind of singular events that turn chance into structure, chaos into pattern. The Earth's encounter with a Mars-sized body, a planet that would later be called Theia, is one of those singularities. It is the most consequential accident in Earth's early biography, and it happened in a physics so vast that human language must borrow metaphors of thunder and ocean to make sense of it. Theia itself was not a mythic invader so much as a sibling in a crowded nursery. In the young solar system, embryonic planets grew in proximity, jostling for the same cantaloupe of material. Theia likely formed in a neighboring orbit, a comparable heap of rock and metal that, by some gravitational nudge or orbital resonance, began to wander toward Earth. There was no intent in this pilgrimage, only the cold arithmetic of orbital mechanics. Small perturbations accumulate, resonances amplify, and two bodies on crossing paths are drawn into an inevitable embrace. To imagine the approach is to think in terms of momentum and inevitability rather than malice. The two bodies were enormous by any human scale, but they moved through space like billiard balls made of incandescent metal. Over days and months they spiraled together, their gravitational wakes tugging at one another, their shapes distorted by mutual pull. The final approach was not a clean head-on meeting, but a glancing, angular encounter, the kind that scatters matter sideways and flings plasma like spray. The energy involved is almost impossible to grasp. The kinetic energy of a Mars-sized object traveling at several kilometers per second converts into heat and force in the blink of a planetary moment. Rocks vaporized, iron liquefied. The sound of that meeting, if sound could travel in vacuum, would have been a roar without parallel. The collision behaved like a compact drama that played out in 3 acts: approach, impact, and aftermath. In the approach, tidal forces began to stretch both worlds, raising temporary mountains and trenches in silicate and iron. That prelude mattered. It primed the contact, setting the geometry for how material would be ejected. In the impact itself, shock waves propagated through mantle and crust at tens of kilometers per second, crushing minerals into new phases, releasing heat so intense that portions of both bodies turned into a superheated, turbulent vapor. Where they touched, material was launched on ballistic trajectories, some slamming back into the planet as incandescent rain, some ascending beyond the planet's grasp and into orbit. The picture that emerges is violent and almost sculptural, an exosphere of molten rock and gas expanding outward, curving into a disk like pottery spun from catastrophic hands. From that chaotic disk of debris, a new body began to assemble. Gravity, indifferent but inexorable, collected fragments into clumps. Clumps collided and merged, shedding angular momentum and smoothing themselves by melting and recooling. Within perhaps decades, perhaps centuries in the terms of planetary formation, the coalesced mass settled into a rounded companion, the Moon. It was born hot, probably partially molten, and set to cool in a courtship with the Earth that would last billions of years. The Moon's formation is one of history's rare double movements, a subtraction and an addition. Earth lost mass and angular momentum. It gained a stabilizing companion that would exert tides, break rotation, and shepherd climatic regularity. The physical consequences for the Earth were immediate and profound. The collision raised global temperatures to levels that likely produced a transient silicate vapor atmosphere, a sheet of rock gas so hot it glowed. Surface materials were melted into oceans of magma many kilometers deep. The crust, whatever fragile stability it had previously begun to muster, was partially obliterated and reformed. The newly rearranged planet had a different spin, a day that was shorter than before the encounter, and a tilt, the angle of the planet's rotational axis relative to its orbital. Plane, stamped by the geometry of the blow. Those two variables, day length and obliquity, would echo into eons, shaping the breadth of climate regimes and the cadence of day and night that life would one day inherit. There is a moral austerity to this scene. If, by some speculative conceit, there had been pockets of chemistry or even early pockets of proto-life before Theia's arrival, the odds of survival were grim. A single trauma of this magnitude is an editor of histories. It erases some drafts wholesale, while allowing others to be rewritten from the debris. They did not merely alter Earth's surface, it reconfigured its narrative potential. The violent erasure it performed also distributed ingredients, water-bearing minerals, organics locked in cometary or asteroidal bodies across a new range of conditions. In that distribution, there is a paradox. The same event that sterilizes can seed. The collision reset conditions, but also provided the raw material that would be available in different contexts to the chemistries that later learned to persist. The moon's early influence on Earth unfurled like a slow, inexorable choreography. The immediate presence of a large satellite altered tidal dynamics in ways that had no analog on a moonless world. Tidal bulges became larger, driving powerful currents in whatever oceans or condensed seas existed after the planet cooled sufficiently. Those currents mixed surface layers in deep reservoirs, preventing the stagnation of chemistry and creating gradients, temperature, salinity, redox that are crucibles for complex reactions. Where tidal forces met young shores and shallow basins, rhythmic wetting and drying could concentrate solutes, bake clays, and allow polymerization events that require alternation rather than stasis. The moon was, therefore, not only a celestial ornament, but a mechanical engine that multiplied the opportunities for chemistry to organize itself into greater complexity. Beyond tides, the moon exerted a stabilizing hand on Earth's obliquity. Without a large satellite, theoretical models suggest that a terrestrial planet's tilt can wander chaotically under the gravitational influence of neighboring planets. Such wandering leads to extreme swings in climate. A planet that might oscillate between mild and glacial states on timescales, destabilizing to any emergent biosphere. The moon's gravitational torque damps those oscillations. By taking some of Earth's angular momentum and establishing a coupled rotational relationship, it preserves an obliquity that allows for seasons, predictable, moderate, and long-lived. Seasons provide another kind of rhythm that shapes ecology, growth and dormancy, migration and stasis. In some narrative sense, the moon bought the young Earth the patience of seasons, a temporal scaffolding upon which ecosystems could reliably build. There were thermal and chemical aftershocks as well. The collision's heat had consequences for volatile retention. Some gases escaped into space in the immediate aftermath. Others were trapped in newly formed minerals or redeposited by later impacts. The exact inventory of volatiles that remained, water, carbon, nitrogen, would determine the atmosphere's composition and the eventual chemistry available on surface environments. The moon itself bears witness to some of these processes. Its low iron core fraction and isotopic similarities with Earth materials suggest that the satellite formed largely from Earth's outer layers, a consequence of the glancing geometry of the collision that preferentially flung mantle material into orbit. That shared isotopic signature is like a forensic trace that links the two bodies' ancestries, and there were longer-term mechanical legacies. The nascent moon, set into an orbit close to the Earth, imparted a tidal braking that slowed Earth's rotation. Days lengthened. Over billions of years, the moon has receded, currently at a rate of roughly 3 to 4 centimeters per year, carrying with it a record of deep time in its steadily increasing separation. That recession altered the balance of angular momentum and subtly influenced the dynamics of Earth's mantle through tidal heating, a source of internal friction that, while small compared to radiogenic heating, could nonetheless tweak convection patterns and magmatic behavior. The combined result is a world whose deep interior and surface climate are entangled not only with the history of heat production, but with the gravitational relationship to its satellite. The visual aspect of the moon's appearance must also be considered for its cultural and, in speculative retrospection, biological significance. A young moon, closer and larger in the night sky, would have been a more dominant presence, a bright, round lantern that governed nocturnal light budgets. Nighttime illumination affects predator-prey dynamics, plant photoreception, and behavioral rhythms. For early chemistries or nascent ecosystems, lunar cycles would have imposed a cadence, a monthly tide of light and dark, of inundation and exposure. Such cyclical constraints are fertile grounds for selection. The moon is both light and calendar. It is an external pacemaker that beats against the internal contingencies of life. One must not overclaim causality here. The moon's existence does not automatically guarantee life's persistence, nor is the moon the sole architect of habitability. What its formation does is reduce the space of catastrophically fluctuating climates and provide recurring physical processes, that expand the repertoire of chemical habitats. In the vast ensemble of planetary possibilities, It nudges Earth toward conditions where biochemistry can run longer experiments without being interrupted by catastrophic obsolescence. It buys time. In the geological sense, that kind of slow, deep time necessary for complexity to accrue. That buying of time, however, came at a cost. The same impact that made the moon also scraped away layers, redistributed heavy elements, and may have boiled off significant fractions of an early atmosphere. It modified Earth's core formation history by stirring deeper melts and mixing materials that might otherwise have been sequestered. It redefined which elements were available at the surface and in what proportions. Those changes were neither good nor bad in a moral sense. They were reconfigurations of the chemical game board. Some pathways to habitability were closed, others were opened. The contingency of the outcome, that Earth would become the blue-green cradle it ended up being, is a consequence of numbers and angles and the luck of orbital timing. There is a human dimension to the moon's birth that invites a particular kind of reflection. All of the everyday rhythms, the length of a day, the steadiness of seasons, the regular advance of tides that would later be plundered by emerging life were, in the deepest sense, artifacts of a catastrophe. The familiarity of the moon in the sky masks its origin as an act of planetary violence. This juxtaposition matters because it reframes a common natural object as the heir of destruction as much as of creation. The moon is a monument to contingency, a fossil of an accident that, by rearranging the scaffolding of Earth's climate and chemistry, enabled the later flourishing of complex life. From the vantage point of deep time, the Theia impact is also a story about narrative pruning. Geological histories are littered with events that close some avenues and open others. The moon-forming collision pruned many potential early trajectories. It could have ended Earth's capacity for habitability, or it could have set the conditions for that very capacity to bloom. The outcome was neither linear nor teleological. It was an instance of selection by catastrophe, where certain configurations were favored simply because they survived the test of violence and persisted long enough to interact with slower, incremental processes. Finally, the formation of the moon is an invitation to humility. The planetary architectures that allow life to persist are not obvious. They are assembled from accidents, resonances, and the slow arithmetic of survival. When the moon rose from the smoke of the impact, it carried away some of Earth's angular momentum and left behind a planet with a different set of probabilities. Those probabilities, summed across billions of years, shaped climates, cycles, and niches. In that sense, the moon is not merely a neighbor, it is a co-author of Earth's story. To think about the Earth Theia encounter, then, is to stand at the seam between destruction and possibility. It is to recognize that singular violence can be generative at cosmic scales, that the logic of catastrophe and creation are entangled. Theia's arrival was a brutal punctuation mark in the narrative of Earth, but it was also a line of syntax that allowed the sentences that followed to become more complex. The moon's birth reoriented the planet's physical habits and opened up novel environmental architectures. Whether one frames this as providence or accident matters less than the simple fact the sky above humanity's earliest ancestors was, in part, a memory of a blow struck billions of years earlier, a memory that still sculpts tides, seasons, and the slow unfolding of life. What does a planet sound like when it is still learning the vocabulary of solidity, when its surface is not ground but a liquid, and every horizon is a furnace? The image is stark and almost cinematic, a world whose daylight is measured not in the gentle temper of air and water, but in the convective churn of molten rock and the furious chemistry of a gas-choked sky. This is the Earth, in one of its most uncompromising moods, a sea of fire, where temperature is not an adjective, but the governing law. The first striking fact about this epoch is scale. The adjective hot feels inadequate when confronted with planetary furnaces. Temperatures were not merely uncomfortable, they were geologically defining. Silicate melts. The very stuffs of crust and mantle flowed as if obeying a different physics, where the modern surface yields basalt that cools into black, solid sheets. The early surface was a viscous ocean, kilometers deep in places, convecting, splashing, and streamlining itself into grotesque and beautiful forms. The air above did not simply warm, it became a plane of incandescent chemistry. Rock vapor rose to mingle with volcanic effusions. Plumes of metal-laden gases swelled and collapsed, carrying with them the smell, if smell could be carried in such an atmosphere, of sulfur and carbon in their most primordial states. This was a theater of continuous eruption. Volcanoes, in the modern sense, were the daily machinery of the planet, but amplified to planetary scales. They were not only localized cones, but whole provinces of upwelling where mantle plumes, unimpeded by a stable lithosphere, burst through into the open. Rivers of molten rock raced across basins, pouring into lower terrains in wide, sheet-like flows that could swallow older features whole. In some places, fountains of lava blew skyward, throwing incandescent droplets that briefly traced arcs of light before splattering into new flows. The soundscape, if sound could be heard through such dense, superheated gases, would have been the long, low rumble of moving mass and the crackle of cooling crusts forming and fracturing, a continuous percussion of creation and destruction. The physics behind this spectacle starts with heat, primordial radioactive decay, latent heat from the coalescence of material, and the kinetic energy of impacts combined to make a planet that was largely molten at its exterior. The convecting magma ocean redistributed heat in chemistry, allowing the segregation of metals and silicates and the gradual establishment of a layered interior. But the surface did not simply sit in molten stupor and cool predictably. It was continually reworked. Each large eruption was a repriming of the surface, each impact a fresh scraping of the canvas. The magma ocean itself was a living skin, thick in some regions, thin and scabbed over in others, forming temporary crustal rafts that drifted, collided, and were readily remelted. The consequences of such a molten world for any nascent chemistry are paradoxical. On one hand, the abundance of high-temperature gradients and mineral surfaces provides a crucible of reactions that are impossible in moderate conditions. At these extremes, unusual mineral phases form, metals alloy, and volatile elements are driven into complex reactive gases. On the other hand, the very violence that forges complexity also erases it. Any fragile, low-temperature assemblies, primitive organics, delicate molecular patterns would be burned, vaporized, or subsumed back into the planetary furnace. Persistence was an exceptional condition in a world that preferred flux. Hovering above the sea of fire was an atmosphere unlike anything that would become familiar in later eons. It was not a gentle blanket of nitrogen and watery vapor. It was instead a dense, turbulent stew where carbon monoxide played a dominant, even defining role. The first air, thick with CO, painted the sky in a different chemistry. This was not merely a matter of composition, but of redox of the electron economy of the early planet. Carbon, under the relevant temperatures and pressures, found itself bound in different species under strongly reducing conditions, where hydrogen and metallic ion are plentiful and free oxygen scarce. Carbon monoxide emerges as a stable gaseous form. Outgassing of the mantle, the thermal decomposition of carbon-bearing minerals, and the liberation of volatiles by impacts all work together to seed such an atmosphere. An atmosphere dominated by carbon monoxide carries implications that ripple through planetary processes. CO is chemically capable. It participates in reactions that can build larger organic molecules when the right catalysts are present. On metal-rich dust grains, on the surfaces of iron-nickel droplets, or along the walls of hydrothermal conduits, CO can be hydrogenated to form hydrocarbons and oxygenated organics in processes evocative of Fischer-Tropsch chemistry. In other words, the very gas that signals a reducing high-temperature world also provides a feedstock for prebiotic synthesis. Given the right microenvironments, with gradients in temperature and redox and the presence of catalysts. But CO also speaks to constraints. It implies an atmosphere poor in free oxygen. It implies a surface chemistry dominated by reduction rather than oxidation. For any would-be chemistry that relies on oxygen or on the gentle dissolution of elements into neutral waters, this was a hostile setting. The greenhouse balance under a CO-rich sky would be different too. CO absorbs infrared radiation less efficiently than CO2 in many bands, but in a dense, multi-component atmosphere where steam and CO2 and other gases also exist, the net effect is still a furnace. The steam from degassing and the bully of CO2, perhaps augmented by methane and ammonia, would conspire to trap heat, sustaining high surface temperatures and allowing molten surfaces to persist for long intervals. The interaction between the sea of magma and the CO-rich air was not merely atmospheric, it was intimate and violent. Wherever molten rock met condensate, if any condensate could exist, there were explosive exchanges. Water, when present, even as transient condensate or as deeply sourced volatiles, flashed into steam upon contact with magma, driving phreatomagmatic explosions that threw ash and glass into the sky. In regions where the surface had begun to scab over into cooler crust, eruptions would punch through, producing packets of gas and molten material that expanded rapidly into the atmosphere. These arrests and reassertions of the crust produce not gentle effusion but fountains, jets, and coronas of incandescent material. The chemistry of the sky during such exchanges was rich in intermediates. Silicate vapor condensed into droplets of glass that rained back across the planet as volcanic glass, beads that would, in later times, fossilize as spherules in ancient deposits. Metal vapors condensed into microspheres of iron and nickel. Sulfurous gases precipitated as aerosols, coating the sky in a haze that modulated the radiation budget in complicated ways. Lightning, a natural consequence of strong convection and charge separation and thick ash plumes, would crack across volcanic clouds, driving high-energy reactions. Electrical discharges provide a potent source of chemical energy, breaking bonds and forging new ones, producing radicals that can recombine into complex molecules. Thus, the same storms that pelted the planet with glass and ash also lit ephemeral laboratories in the sky. There is a temporal dimension to these processes that magnifies their meaning. One must not imagine the Sea of Fire as a permanent state. It was a chapter with a slope. Over geological durations, the planet's mantle cooled, the frequency of large impacts diminished, and degassing evolved. Yet the transition was long and patchy. Cold spots emerged, pockets of crust and basement that lingered longer than their surroundings, and these provided refugia where less violent chemistry could proceed. In these refuges, CO-rich atmospheres could thin locally as gases reacted with minerals or were sequestered into newly formed compounds. Water, when it managed to persist, could act as a solvent for chemistry, albeit one that was often superheated and acidic by modern standards. The redox evolution of the atmosphere is crucial. In a CO-rich early atmosphere, photochemical reactions driven by intense ultraviolet light from a younger sun could break CO into carbon and oxygen radicals. Those radicals, in turn, could recombine in various ways, producing CO2, depositing carbon as soot, or polycyclic structures, or forming simple oxygen-containing molecules. But the story does not move toward free oxygen in any linear fashion. Free oxygen, should it appear, would be immediately mopped up by vast reservoirs of reduced iron and other electron-seeking minerals. The young crust and mantle were vast sinks that absorbed oxidants. Thus, even if oxygen were tellurally produced in trace amounts, the planet's chemistry conspired to keep the air reduced for an extended period. This chemical stubbornness matters to the question of habitability in a broad sense. A CO-rich atmosphere paired with a molten surface is not hospitable to the kind of aqueous, near-neutral chemistry that modern life depends upon, yet it is a crucible for different pathways. Metallurgic catalysts, hydrothermal gradients beneath thin crustal lids, and episodic coolings could create narrow windows where complex organics accumulated and survived. The volatility of the environment meant that long-term persistence was rare. But persistence is not a binary attribute. Even intermittent stability, repeated across millions of years, can be sufficient for complexity to cross thresholds. There is also the question of retention. How did such a dense reactive atmosphere avoid being stripped into space? Part of the answer lies in the enormity of the atmosphere itself. A heavy atmosphere, a pressure blanket measured in tens or hundreds of bars rather than the single bar of today, provides inertia against solar wind erosion. Additionally, the partial development of a magnetic dynamo, as iron segregated and convected in the core, granted some protection. The young sun might have been more boisterous, but the planet was not naked. Layered defenses, in the form of a dense gas envelope and an incipient magnetosphere, gave the early atmosphere time to evolve instead of being instantly lost. From the vantage of human reflection, the Sea of Fire and the carbon monoxide sky deliver a lesson in planetary temperaments. The conditions that, in many ways, threatened the emergence of life also supplied the very raw materials and energy gradients that make complex chemistry possible. The same eruptions that vaporized nascent organic assemblies also exposed fresh minerals and catalyzed new reactions. The lightning that shattered bonds also wrote new ones. In the long trajectory of Earth's history, catastrophe and provision coexisted. The planet was, in effect, testing a myriad of chemical experiments at once, discarding the ones that failed and, without purpose or design, allowing the occasional fragile success to persist into quieter epochs. As the planet cooled and the intensity of eruption waned, the Sea of Fire did not simply vanish, but reorganized. The magma oceans receded to a more conventional interior. Crust thickened and began to behave like the skin it would later be. The atmosphere slowly moved through different dominances as chemistry and physical escape reshaped its composition. CO, while dominant in the earliest breaths, would be gradually oxidized and sequestered, its prevalence a signpost of a very particular moment. The transition from a CO-heavier air to a mixture where CO2, N2, and later traces of free oxygen appeared, marks one of the pivotal shifts in Earth's chemical biography. It is the hinge between a planet of fire and a planet of temperate possibility. In the end, the sea of fire is as much a metaphor as it is a geological fact. It is a reminder of the precariousness of stability and the stubbornness of materiality. Above the molten seas, under an atmosphere of carbon monoxide and volcanic steam, the processes that would eventually make a habitable world were being trialed in extremes. The scene is terrifying and beautiful in equal measure, a planet for which continuity of surface was not guaranteed, yet one whose inner rules, heat flow, differentiation, and chemical partitioning were being etched with indelible force. The listener is left with a twin sensation, awe at the scale of material flux, and a peculiar consolation. From this ancient furnace, through processes that alternate between annihilation and synthesis, would emerge a world capable, eventually, of sustaining the delicate economies of life. The sea of fire is, therefore, both an ending and a beginning, the closing of one set of possibilities and the opening of another, quieter chapter that will later be read as the beginning of habitability. What does it mean when the sky itself is a factory and a firing range at once, an expanse that gives off steam and lightning, where gas and rock collide in a daily liturgy of creation and erasure? That image frames a chapter of Earth's biography that is equal parts chemist's workshop and battlefield, an age before oxygen, under a brooding, layered heavens thick with steam, methane, ammonia, and toxic exhalations, an age in which meteors did not fall as rare curiosities, but as the steady punctuation of planetary life. The composition of that sky is decisive in the story it tells. In the interval after the magma oceans began to cool and before stable atmospheric equilibria had the leisure to form, the air was less a breathable medium than an alchemical soup. Water vapor rose in vast plumes from degassing interiors. Hydrogen, set free from mineral lattices and delivered by icy bodies, drifted aloft. Methane and ammonia, hydrocarbons and nitrogenous volatiles swelled in the lower atmosphere where reducing. Conditions persisted. Carbon monoxide and carbon dioxide shared this stage, and sulfurous gases lent a sharp, corrosive edge. Free oxygen was absent. The planet's electron economy ran toward reduction. This was not merely a different recipe for air, it was a reordering of chemical possibilities. The visual of such an atmosphere is not pastoral. Layers of thick clouds, some laden with condensed steam, others choked with soot and volcanic aerosols, knitted the sky into a continuous dome. Light was muted and diffuse. The sun, younger and more ultraviolet rich, still pierced with an ultraviolet knife, but its visible warmth was filtered through hazes and veils. Within these clouds, storms were primal and relentless. Convection drove towering electrostatic separations. Charge arcs leapt across ash-rich plumes and across vapor-laden columns. Lightning was not occasional, but systemic. A persistent agent of high-energy chemistry, lightning in a reducing atmosphere is chemical theater, where bolts crack across hydrogen, methane, and ammonia-rich air. Molecular bonds are torn asunder and recombine into new assemblies. The lesson of mid-20th century experiments, the dramatic Miller-Urey tests and their successors, was not a demonstration of inevitability, but of possibility, given the right gases and the right energy inputs. Amino acids and other organic precursors can appear from lifeless chemistry. In the ancient storms, lightning and ultraviolet photons, together with hot catalytic surfaces, could produce hydrogen cyanide, formaldehyde, simple sugars, and a plethora of hydrocarbon chains. These molecules, fragile in the face of heat, nonetheless accumulated in droplets, aerosols, and on particulate surfaces. The sky thus functioned as a producer of raw biological ingredients, even as it remained inimical to long-term survival of delicate assemblies exposed on the open surface. But electricity was only one of many energetic forces at work. The planet below the clouds was under a constant hail of extraterrestrial material. For millions of years, meteoroids, comets, and small asteroids did not come as rare visitors, but as habitual guests. These bodies range from dust-sized micrometeoroids to multi-kilometer projectiles. Each scale produced different consequences. The smaller particles, the cosmic quit, ablated as they plunged through the thick skies, their outer layers melting and vaporizing, creating incandescent trails and delivering metal-rich vapors to the atmosphere. The larger bullets punched craters, launched plumes of vaporized rock, and generated local annealing furnaces where temperatures and pressures spiked for brief, intense intervals. The continual rain of meteoritic material had a dual character. On one hand, it was a relentless, erosive, and destructive force. Impacts shredded nascent crusts, sterilized surfaces by heating or ejecting them, and periodically reset local chemical experiments. On the other hand, it was a conveyor belt of novelty. Many meteoroids were carriers of organic carbon and of preformed amino acids. Water ice within comets delivered fresh volatiles. Metallic cores provided catalytic surfaces rich in iron and nickel. Each impact was, in that sense, both an editor and a donor, a violent act that often closed a local chapter but also scattered new ingredients into the next. A single micrometeorite entering a dense, reducing atmosphere is a miniature drama. It begins as a cold, distant rock. As it encounters the thick air, friction and compression ignite its outer shell into plasma. Metals within it liquefy and volatilize. Tiny spherules of iron and silicate condense from the vapor and rain down as glassy beads, recording in their chemistry the brief furnace through which they passed. Aerosols generated by this process, seed clouds, alter radiative balance and offer surfaces for gas phase molecules to stick and react upon. On larger scales, when a stony projectile strikes a shallow basin or a cooling crust, the impact excavates material from depth, exposing fresh mineral interfaces and generating hydrothermal circulation in the aftermath. Where an impact penetrated to heat groundwater, a chimney of hot fluids could persist for centuries, hosting gradients of temperature and redox potential, ideal microenvironments for synthetic chemistry. Those hydrothermal systems deserve emphasis. They are the quiet counterspeech to the spectacular violence above. As the surface was hammered and reheated, interior heat drove water through fracture networks. In these convective smearings, mineral-rich fluids met cooler surrounding rocks and precipitated minerals with catalytic properties, iron sulfide chimneys, transition metal minerals, and clays. Such surfaces concentrate organic molecules, orient them, and occasionally catalyze polymerization. The meteor-delivered metals were not simply passive particulates. They acted as heterogeneous catalysts, enabling reactions that might be improbable in an unassisted gas phase chemistry. In other words, the bombardment, while disruptive, increased the chemical complexity of the stage. The compositional interplay between atmosphere and falling material produced a shifting palette of chemistry. A hydrogen and methane-rich sky is more conducive to forming complex hydrocarbons and nitriles when struck by energy. Ammonia and hydrogen interplay with ultraviolet radiation and lightning, favored production of nitrogenous organics, key constituents of nucleobased precursors. When meteoritic dust carried organic compounds into this environment, it mixed preformed molecules with freshly synthesized ones, creating heterogeneous soups where complexity could accrete. Rain, not merely of water but of molten spherules, ash, and condensed organics, washed these mixtures into basins and shallow puddles, concentrating solutes in cyclical ways. Here, the mechanics of concentration matter. The early Earth lacked long-lived rivers and stable coasts in the modern sense, but it did have tidal flats, ephemeral pools, and searingly hot shoreline gradients where dry, wet cycles could occur. The moon's presence, born of prior catastrophe, had already established tides of considerable power. Where tidal inundation met volcanic or impact-heated shorelines, rhythmic wetting and drying could drive polymerization, as solutes concentrate and then are baked by heat. The meteor rain fed those basins with fresh material. Ash and spherules provided mineral surfaces for adsorption and catalysis. In a world of repeated destruction, these small, repeated opportunities of concentration were the experiments that mattered most. The atmosphere itself was not a monolith, but a set of gradients and layers. High in the sky, ultraviolet photochemistry transformed methane and ammonia into complex hydrocarbons and aerosol precursors, prebiotic analogues of Titan's orange haze. These photochemical hazes settled, coating the surface and shading it from some ultraviolet influx, but also bringing down complex organic compounds. Closer to the surface, steam and sulfurous gases reacted with metal-rich dust to form sulfides and to sequester oxidants. The net effect was a kind of chemical zoning. The upper atmosphere is a reactor for long-chain organics, mid-level storms as synthesis and transport agents, the surface and near subsurface as concentration chambers and catalytic beds. Yet the absence of oxygen was decisive and persistent. In a reducing world, oxygen's reactive appetite finds little to consume. Conversely, oxygen that might be formed transiently by photolysis was quickly claimed by abundant reduced iron and sulfur in the crust. The result is an environment in which free oxygen would be a latecomer, and where chemistry evolved in pathways unfamiliar to later oxygen-rich metabolisms, that is both a constraint and an opportunity. Where oxygen-based energy economies would later define complexity, this era allowed other redox chemistries to flourish. Hydrogen and sulfur cycles, methane photochemistry, and iron-driven reactions. For any talk of habitability, the listener must learn to decouple habitability from likeness to modern life. The early Earth taught that life, if it were to arise, would have to be confident in odd currencies, hydrogen gradients, sulfur fluxes, and iron catalysis. There were also global-scale consequences of the persistent meteor rain. Repeated impacts stirred the mantle and shallow lithosphere, promoting outgassing and the injection of volatiles into the atmosphere. Massive bombardments could strip parts of the atmosphere into space, particularly when a large projectile vaporized large volumes of gas and accelerated them beyond escape velocity. Yet the atmosphere was not simply lost. Dense envelopes of steam and carbon-rich gases provided inertia. Recent work has suggested that a nascent magnetosphere, generated by a convecting metallic core, furnished an additional shield against stellar wind erosion. The balance between gain and loss, between delivery of volatiles and stripping of atmosphere, was a negotiation written in impact statistics and in the strength of planetary defenses. One way to think about the meteor rain is to view it as a source of repetition and variation. Each impact is a rerun with small changes, different composition, different energy, different target. Over millions of years, this statistical ensemble produces rare configurations, a particularly fortuitous sequence of impact delivery and local stability that allows a chemical system to persist long enough to cross thresholds of complexity. The listener should imagine the deep time equivalent of natural selection operating not on organisms, but on chemical niches, a selection of environments that, by accident and endurance, become better at preserving complexity. There is an aesthetic and ethical poignancy in this scene. The ancient sky, heavy with hydrocarbons and charged with constant lightning, was both hostile and fecund. It was a place where synthesis occurred without intent, where the energy to build complexity was abundant, but persistence was scarce. Continuous bombardment made the planet an unruly workshop. Raw materials were abundant, but the workbenches were repeatedly smashed. If life eventually took hold, it would not have been because the universe was benign, but because it was generous and brutal at once, offering an abundance of trials and only occasionally permitting a composition to persist. This balance between creation and destruction is a refrain throughout early Earth history. The meteoritic rain did not announce itself with a single cosmically romantic event. It acted as a sustained pressure. Over time, as the flux of extraterrestrial material decreased and the planet's surface gained more robust crust and more stable water reservoirs, the frequency of sterilizing impacts waned. The thick clouds thinned in places. Lightning continued but became less meteoric as a formative agent. Yet the imprints of that incessant rain remained. Glassy spherules trapped in ancient sediments, isotope anomalies in crustal minerals, and the catalytic distribution of metals across early basins are all fossil memories of a sky that once rained rocks as often as water. To imagine this chapter vividly is to feel a profound smallness. Human histories are candle-length flickers compared to the epochs of bombardment and cooling, yet the very conditions that could have gestated life were sculpted within those long intervals. The meteor rain is a reminder that planetary habitability emerges from the tension between accident and selection, between an abundance of destructive events and the rare, patient stability that can follow them. The sky, a Spectrian firing range, leaves an ambivalent inheritance. It provides both the raw ingredients and the trials against which those ingredients were tested. In the end, the narrative of meteoritic rain is not one of simple doom, but of audition, a long audition in which Earth's chemistry rehearsed countless possibilities until, in a later act, a few experiments were granted the time to become something more than chemistry. In that quiet moral, the chapter closes with a hinge into what comes next, an Earth gradually relieved of its most savage fireworks, still shrouded by clouds and charged with volatile chemistry, but increasingly capable of holding on to the delicate assemblies produced by lightning and dust. The meteors, having done their work of delivery and upheaval, begin to thin, and in their wake, the conditions that favor persistence, pools that can concentrate organics, mineral surfaces that catalyze polymer formation, and climates that allow longer, uninterrupted experiments, begin to appear more frequently. The story is not yet about life, but it is, finally, about the possibility of it, the slow, improbably patient accrual of conditions that make the leap from chemistry to biology less mystical and more simply possible. What does it mean for a planet to stop being a belligerent furnace and, for the first time, let its sky collapse into rain? The question is small and precise, a hinge in deep time, but it opens onto a cascade of transformations that will, in due course, redefine what a world can do. The arrival of water on the young Earth is not a single heroic moment, but a long negotiation. Between violence and surrender, comets and asteroids delivering life's raw ingredients while simultaneously battering and boiling them away, an atmosphere heavy with steam slowly losing its heat until the first droplets can survive the fall, basins carved by impact and tectonics learning, at last, to hold liquid rather than lava. The formation of the first ocean is, in the simplest sense, a planetary act of mercy, a transition from a planet dominated by thermal flux to one where liquid water can persist on the surface long enough to matter. The suppliers were both generous and cruel. In the crowded nursery of the early solar system, icy bodies moved inward from the cold reservoirs beyond the frost line, and rocky, volatile, rich meteorites wandered inward from slightly closer orbits. Each comet, each carbonaceous chondrite, was a capsule, water bound as ice, volatile gases trapped in minerals, organic compounds pre-assembled by chemistry in the dark beyond the sun. When these bodies collided with the young Earth, they delivered water and minerals that the planet did not yet possess in abundance. But the deliveries arrived to a planet that, for a long time, was not ready to receive them. High-speed impacts produced instantaneous furnaces, kilometers-wide plumes, global vapor clouds, and shock waves that could temporarily vaporize existing surface water. In short, the very processes that seeded Earth with water also risked stripping it away. The balance between delivery and loss was a matter of scale and timing. Small, frequent deliveries, a steady rain of dust and micrometeorites, could accrete water incrementally, embedding volatiles into soil and rock. Large, rare impacts were paradoxical, catastrophic in their immediate effects, but also capable of setting long-term conditions. A collision that excavated a deep basin might later provide the perfect low place to collect condensed steam, a strike that. Vaporized local reservoirs might also mix new chemical species into the atmosphere that would later condense as part of a more chemically diverse ocean. The planet was learning, through a sequence of violent lessons, how to retain what it had been given. As the Earth's interior cooled and the frequency of the most catastrophic impacts lessened, an inflection occurred. The great steam blanket that had cloaked the planet began, very gradually, to collapse. This was not a single downpour, but a geological condensation. The atmosphere lost heat through radiation and convection, and gases that had been locked as vapor began to collect into droplets. High-altitude clouds thickened and then finally produced sustained precipitation. The first rain was not benign. It fell through an atmosphere choked with sulfur, carbon dioxide, methane, and ash. It was often hot and acidic, a corrosive scouring of nascent rock and glass. Yet even this brutal rain had a gift. It transported dissolved minerals, concentrated organics, and set into motion erosion and sedimentation, the processes that would lay down the first sediments, the first chemical records that would survive through time. There is a striking paradox in imagining those first waters. To modern sensibilities, oceans are kind and stable. They temper climate, cradle life, and present infinite horizons. The primordial seas were none of these things at first. Physicists and geochemists mostly agree that the early oceans were shallow relative to later depths, basins perhaps hundreds to thousands of meters deep rather than the modern average of nearly 4 kilometers. The chemistry would have been extreme, acidic where volcanic gases dominated, ferruginous where iron poured into waters unopposed by oxygen, and silica-rich where rapid weathering of fresh crust liberated dissolved silica in copious amounts. The water itself, while plentiful in places, was chemically alien, anoxic, cloudy with suspended mineral particles and volcanic glass, a liquid that would have been hostile to modern life, yet fertile for a different kind of chemical invention. Where the first ocean formed mattered as much as when. Impact basins created depressions large and deep enough to become early seas, low-lying lava plains that had cooled faster than. Surrounding areas trapped rain and runoff. Tectonic topography, in its earliest and most chaotic forms, produced isolated ponds and rift basins where water could concentrate. The moon, born from earlier catastrophe, had already begun to exert tidal forces that would mix shallow coastal waters. Those tides, strong by comparison to later epochs, amplified contact between water and rock, creating cycles of wetting and drying along primitive shorelines. The convergence of tidal mixing, hydrothermal activity, and sedimentary concentration was crucial. It produced gradients in salt, temperature, and pH that are the raw power for chemistry to become more than chemistry. Beneath the surface, where hot rock met cold water, hydrothermal systems began to flourish. These systems are among the most important consequences of the ocean's formation. As water penetrated the hot lithosphere, it circulated through fractures, reacted with minerals at high temperature, and returned to the ocean fed with dissolved metals, reduced compounds, and thermal energy. The resulting chimneys, mineral precipitates built around effluent plumes, concentrated metals, and provided catalytic surfaces, where simple organic molecules could interact and assemble into larger structures. If the surface rain and shallow pools were the suppliers of organic building blocks, then the vents were the workshops where those blocks could be refined and recombined under sustained, steep chemical gradients. The chemistry of those early seas is, in one sense, a catalogue of scarcity and plenty. Oxygen was absent, so iron remained soluble in reduced forms and could be delivered in high concentrations as ferrous iron. Silica was abundant, precipitating as amorphous silica and forming layers of chert in later sediments. Carbon existed as CO2 and CO and as dissolved organics. Nitrogen appeared in various reduced forms when it was delivered, but free nitrate or abundant oxidized nitrogen would be almost unheard of. Metals, iron, nickel, molybdenum, copper, arrived variably either sequestered in the mantle or added by meteorites. The net effect was an ocean capable of supporting a suite of redox reactions unfamiliar to modern, oxygen-rich biology but ripe for different metabolic chemistries, sulfur cycling, iron reduction, methanogenesis in later epochs. Those early reactions would not resemble modern life outwardly, but they would establish the deep, energetic patterns that life would later exploit. Timing matters. New geological clues suggest that liquid water may have been present on Earth far earlier than classic narratives, allowed, perhaps slipping into the scene within a few 100 million years after the planet's formation. Zircon grains preserved in ancient rocks bear isotopic signatures consistent with interaction with liquid water as early as 4 billion years ago, whispering of temperate pockets in a world otherwise known for heat. Other signatures, like hydrogen isotopic ratios in minerals, beg the question of provenance. Did most ocean water arrive with comets, or was it delivered by water-bearing meteorites from nearer the asteroid belt? The science does not yet settle the argument definitively. It offers instead a spectrum of possibilities and a lesson in contingency. Either route, cometary bombardment, or asteroidal accretion emphasizes the same idea. Water's presence on Earth was contingent on external delivery and internal retention, a partnership between the planet and its neighborhood. The presence of an ocean was not only a chemical watershed, but a geological one. The ocean became an agent of erosion and of deposition. Rain and rivers, once stable enough to persist over geological spans, carved channels, carried sediments, and began the process of layering that would form the first sedimentary archives. Those archives, in time, would record the earliest steps of the planet's chemical and tectonic evolution. Traces of oxygen's gradual rise, evidence of early microbial metabolisms, the fingerprint of impacts, and the slow assembly of continental crust. But those archives were fragile at first. Repeated impacts, volcanic resurfacing, and crustal recycling meant that the earliest records were often overwritten. The few grains that survived, like the resilient zircons that speak to ancient water, are treasured because they are exceptions, tiny centers of continuity in a world that preferred to remake itself. There is also a climatic dimension to the first oceans. Liquid water increases the planet's capacity to moderate temperature through heat uptake and transport. The nascent hydrosphere allowed heat to be redistributed from equator to poles and from day to night, diminishing some of the extreme thermal gradients that had characterized earlier epochs. Once oceans could persist, clouds and evaporation introduced new feedbacks into the climate system. Reflective cloud decks could cool the surface, while greenhouse gases dissolved in seawater could either trap heat or, through chemical weathering, be sequestered into long-term sinks. These feedbacks did not produce stability overnight, but they did create the conditions for longer, sustained climatic intervals, the kind of steadiness that made the emergence of persistent chemical systems and later life more probable. There is a human temptation to read the arrival of oceans as inevitable and clean, a line drawn neatly between hot and habitable. The reality is messier and, in many ways, more dramatic. The ocean's birth is a story of persistence against erasure. Water poured in, was vaporized by impacts, returned again, and slowly accumulated as the planet learned to keep its gases rather than letting them go to space. It is also a story of paradox. The same impactors that threatened habitability also carried the seeds of it. Each comet and meteor was both donor and destroyer, and the ocean is the ledger of that ambivalence. Finally, the first ocean is a moral image in miniature for anyone who contemplates it. It stands for vulnerability, made powerful. A shallow, acidic, iron-laden sea is not, by modern standards, hospitable, yet it is exactly the kind of environment where novel chemistries could find purchase. From conditions that are imperfect, even hostile, complexity can emerge, given time and repeated opportunity. The ocean's formation forced a new kind of temporal patience onto the planet. It created a medium in which chemical processes could persist long enough to explore combinatorial space, to amplify rare events, and to generate boundaries between inside and outside. Those boundaries, membranes, gradients, compartments, are the prerequisites of life. To picture the scene is to acknowledge scale and humility. An individual storm, an isolated impact, a single volcanic eruption. They seem monumental. Over the vastness of deep time, they become moments in a patient accumulation. The first ocean is not a single miracle, but the slow arithmetic of delivery, retention, cooling, and reaction. It is the product of a neighborhood that supplied volatiles, a planet that learned to hold them, and processes that converted transient chemistry into something that could persist. In that persistence lay the real miracle, a place where matter could circulate, concentrate, and sometimes, against all odds, begin to tell itself new kinds of stories. The first ocean is, therefore, less an endpoint than a threshold, the threshold over which the world crossed from molten experiment to aqueous workshop, a place where the next chapters of the planet's narrative would be written in currents, sediments, and the slow inventiveness of chemistry. What happens when rain does not come as a single polite event, but as a geological sentence that repeats itself for millions of years? That question is small and sharp, and yet it opens onto some of the most consequential motions in Earth's biography. To let steam condense into persistent precipitation is to change the rules of a planet. It converts ephemeral vapor into persistent reservoirs, temporary basins into seas, and chemical possibility into an ongoing experiment. The first long rains were not a mercy so much as a redefinition. A world that had been dominated by heat and vapor began, stubbornly and slowly, to admit liquid into its grammar. The first drops that survived the fall were not the soft, nourishing rains imagined by poets. They began as scalding torrents, drawn from an atmosphere full of steam and volcanic emissions. For perhaps millions of years, precipitation arrived through layers of sulfurous mist and carbon-rich haze. Early droplets carried dissolved gases and mineral acids. They hit the ground and reacted with molten glass and fresh basalt. Where water met cooled lava, explosions followed, violent phreatomagmatic eruptions that sent glassy spherules back into cloud. Where water infiltrated fractures, downstream hydrothermal circulation began, a subterranean plumbing that would later be essential to chemical synthesis. But even corrosive and hot, rain concentrated molecules, moved them, and deposited them. It was a sculptor as well as a scourge. This relentless downpour performed two crucial tasks. First, it washed and redistributed the planet's raw materials. Steam condensed, droplets fell, and dissolved ions, iron, silica, calcium, sodium, were carried downslope into low basins. Those ions would precipitate or remain dissolved, setting the chemical tone of the nascent seas. Second, precipitation enabled the first real sedimentary processes. Weathering began, not as a long, green-driven cycle, but as physical and chemical erosion of very young crustal surfaces. Fresh volcanic glass and crystalline minerals were ground into powders by impacts and thermal fracturing. Rain gathered these fines and carried them into hollows and craters, laying down the first layered sediments. Where impact basins collected water and fines, shallow, turbid waters formed, patchworks of mud, silt, and ash pressed into the earliest stratigraphies. As water pooled and persisted, distinct microenvironments emerged. Shallow coastal shelves alternated between wet and dry as tides, amplified by the youthful, closer moon, battered marginal areas. These rhythmic exposures concentrated solutes and baked organics in cycles of evaporation and rehydration. In deeper basins, slow settling allowed fine particles to accumulate in laminae, while hydrothermal vents beneath the water column continually supplied reduced minerals and heat. In each of these niches, the chemistry of aqueous media was different, and each offered distinct opportunities for increasingly complex reactions. Where land and sea met under tidal influence, the alternation of saltwater bathing and evaporation created chemical crucibles that would later be invoked in many origin hypotheses. The relentless rain thus became an architect of gradients, gradients in concentration, temperature, and redox potential, the conditions that convert static chemistry into productive reaction networks. It is important to hold two images together, the violence of the initial condensation and the slow, cumulative tenderness of continued rainfall. A single scouring storm could sterilize a shallow pool, boiling it nearly to its margins, while a long succession of milder rains could leach metals out of basalt and feed long-lived hydrothermal systems. Over hundreds of thousands and then millions of years, the net effect was an increase in persistence. The atmosphere cooled, more steam condensed, and the hydrosphere grew from scattered puddles and basins into contiguous bodies, seas that began to regulate temperature and redistribute chemical wealth across broad scales. The first liquid water bodies were not immediate havens. They were chemically primitive, often acidic and rich in dissolved iron, silica, and sulfur compounds, yet they formed the wet stage upon which more elaborate chemistries might play out. The geological record is fragmentary because much of it was reworked, buried, or melted, but the surviving hints are eloquent. Zircons older than 3 to 4.4 billion years, whisper that pockets of crust cooled enough to interact with liquid water very early. These durable mineral grains, coded in isotopic signatures of oxygen and hafnium, suggest that liquid water and a relatively cool crust were not latecomers but partners in Earth's youth. The very existence of these mineral storytellers demands a reinterpretation. Rain, however violent at first, had already established pockets of quiescence. Those pockets were the seeds of an aqueous planet. From condensation to permanence, the formation of a recognizable crust. If the first rains rewrote the surface language, the formation of the solid crust rewrote the planet's structural grammar. Where once the outer shell had been a shifting film of molten silicate, a magma ocean in convective motion, cooling, and chemical differentiation began to produce durable lithosphere. The emergence of a solid crust was not a single event, but an accumulative process of cooling, fractional crystallization, and repeated reworking by impacts and volcanism. The result, over the deep span of geological time, was a layered planet, an interior that still convected and an outer skin that could break, float, accrete, and persist. Two related processes were central. One was the solidification of the magma ocean in broad terms. As the planet radiated heat to space and as radioactive decay slowed, the outer layers began to freeze. Crystallization produced mineral phases that sank or floated depending on density, resulting in compositional layering and the initial segregation of a primitive crust. The other equally crucial process was remelting and differentiation on smaller scales, localized partial melting of basaltic upper mantle or reworking of accumulated volcanic piles into more silicic compositions. Over time, repeated melting, fractional crystallization, and the buoyant rise of silica-rich melts produced early forms of continental crust, less dense, more granitic in composition, and capable of persisting above the denser oceanic basalt. The water that fell in so many storms played an underappreciated part in this crustal evolution. Water lowers the melting point of rock. When water infiltrates into the lithosphere, whether through fractures, hydrothermal circulation, or subduction-like processes, it facilitates melting at lower temperatures, enabling the generation of silica-rich magmas from a predominantly basaltic mantle. In a world where water had begun to persist on the surface and to penetrate into fractures, the conditions for differentiated, buoyant crust became more favorable. Hydrothermal alteration of the upper lithosphere changed its mechanical properties and chemical makeup, making portions more susceptible to partial melting and detachment. Thus, the hydrosphere and the emerging crust were in active conversation. Rain and oceans helped produce chemical and mechanical environments that favored the formation of long-lived continental fragments. Yet crustal formation is not a peaceful accretion. Early crust was continuously threatened by impacts and by the planet's own internal vigor. Large collisions could remelt crustal patches, return material to the mantle, and reset portions of surface history. Frequent volcanism resurfaced expanses of basalt. The result was a dynamic patchwork. Protocontinents, small, buoyant crustal blocks, formed, accreted, and were recycled, a process that would repeat over billions of years. The earliest continental nuclei were likely small and scattered, tiny archipelagos of silica-rich land amid a global basaltic sea. These islands were the first places where weathering would operate on rocky surfaces more consistently, where soils had the possibility of beginning in a primitive form, and where sediments could accumulate in stable enough basins to become the planet's first sedimentary archives. Geochemical fingerprints confirm this narrative. Ancient isotopic anomalies preserved in the rare surviving rocks and in zircons point to early crustal reworking in the presence of differentiated crust as far back as 4 billion years ago. The nature of early granitic suites, so-called TTG, tonalite, trondhjemite, granodiorite rocks, suggests that wet basaltic source rocks were melted to produce more silica-rich magmas. Those TTG suites are the scaffolding of early continental crust, buoyant, resistant to erosion and recycling, and essential to the long-term development of continents. But how, precisely, such melts were produced remains debated. Mechanisms range from early forms of subduction to plume-driven melting and intercrustal reworking. The debate itself is evidence of a planet in flux. Earth was experimenting with tectonic regimes before settling into the more familiar plate tectonic style of later eons. This experimentation had consequences beyond mere rock types. The earliest crustal forms influenced climate and chemistry by providing new sinks for atmospheric constituents. Weathering of nascent continents removed CO2 from the atmosphere, binding it into carbonate minerals that would be stored in sediments. This process, slow at first but cumulative, provided a planetary thermostat. By sequestering greenhouse gases, weathering could cool the atmosphere gradually, promoting further condensation and stabilization of oceans. In this way, the lithosphere and the atmosphere entered a feedback loop. Crustal emergence encouraged processes that tempered the atmosphere, and a tempered atmosphere allowed more durable crust to survive. The interplay between the physical and chemical systems was a deep-time negotiation. The structure of the early crust also determined the fate of memory. Rock is the planet's archive, but it is also its eraser. Where crust was thin and frequently remelted, the record of early chemistry and early events is scoured away. Where crust thickened and became continental, there was a higher chance that local histories could be preserved in layers of sediment, in mineralized veins, and in resilient crystals like zircon. Thus the very process of crust formation was also a filter on what deep time would remember. A violent adolescence erases possible chapters. Stabilizing crust permits the accumulation of chapters. The persistence of a robust plate of continental crust is what allows long-term records of atmospheric composition, hydrology, and even early life to be written and preserved. The morphological consequence of these processes can be imagined as a slowly coalescing mosaic. In the beginning were small rafts of crust, largely basaltic but occasionally punctuated by more silica-rich domes. Over time, through accretion and chemical differentiation, these rafts welded together into larger blocks. Collisions between rafts raised folded mountain belts, the early analogues of continents colliding, while intervening basins, filled with sediments delivered by rain, rivers, and tidal action. The first true cratons, thick, stable, and buoyant lithospheric keels, likely formed through such prolonged assembly and became the deep anchors of later continents. Where cratons survived the errors of reworking, they preserved a deep time memory in their internal isotopic structure. Where they did not, their stories were lost in recycled magma. One paradox of crust formation is how destructive and conservative processes are intertwined. Partial melting and fractional crystallization are agents of novelty. They create new rock types, set up compositional differentiation, and allow buoyancy-driven segregation. But recycling by tectonics and impacts is conservative in a different sense. It reduces diversity by remelting and homogenizing pools of material. The history of Earth's crust is therefore a balance between these twin tendencies. On the one hand, new crustal compositions and configurations emerge. On the other, many of these novelties are short-lived and seldom fossilized. The record that survives is thus selective, biased toward those patches of crust that congealed into enduring forms. In practical terms, the formation of a solid, stable crust meant new opportunities for chemistry and for later biological innovation. Solid shores could host tidal flats, islands could provide weathered rock for nutrient delivery, buried hydrothermal systems beneath insulating crust could maintain stable gradients for long durations. Each of these settings is a stage for increasing chemical complexity. It is easy to romanticize continents as the locus of life's origins, but the truth is more nuanced. The interplay between water, heat, and crust, in shallow and deep settings alike, created a distributed landscape of potentiality. Life, when it finally emerged, would do so within a tapestry woven from rainfall, seas, vents, and crustal fragments. To watch crust form in deep time is to watch a planet learning to keep its history. As layers of rock hardened and as continents floated and collided, Earth acquired the capacity to store, protect, and recall episodes of its own past. Rain that once fell to be immediately vaporized now soaked into rock and soil, making pathways for chemistry that could not previously exist. The crust thereby became both a stage and an archive, a place where the conditions for life could be sustained and where its earliest footprints might eventually leave detectable traces. The formation of the crust is not the end of a story but a hinge into subsequent chapters. It is the slow conversion of a planet from a volatile experimenter into a conservator of processes. In the presence of durable lithosphere, the hydrosphere could become steadier, atmospheric chemistry could be regulated by. Weathering and hydrothermal systems could persist on timescales long enough to allow rare chemical victories to be codified. For any listener trying to follow the arc of possibility, the crust's arrival is the moment when contingency shifts toward accumulation. The planet ceases to be a furnace that continually remakes itself and becomes, instead, a world that can hold on to its experiments long enough to let complexity arise. What does a planet become when its skin finally decides to stop flowing? That question sits like an ache in the long body of deep time, a moment in which flux gives way briefly to form a tenuous crust that can support weight, hold water, and begin to remember. The answer, however, is not simple or tidy. The first cooling of Earth's brittle shell was less an arrival than a negotiation, and the loudest voice in that negotiation was fire. Volcanoes did not merely punctuate the planet's adolescence, they authored its grammar. In their eruptions, the planet both destroyed and conserved, erased and wrote anew. For a time, the crust was a fragile seam, a mosaic of flows and rafts that had finally cooled enough to behave like rock rather than ocean. These pieces, proto-continents if one must name them, rose and drifted like the flows of an incandescent sea. They were small and short-lived by the standards that would later define continents. Islands of buoyant, silica-rich lithosphere adrift on a convecting mantle. Their boundaries were not neat lines, but ragged seams, places of constant repair and failure. Between them, the planet's interior still pressed and pulled, upwelling magma in some places, folding and sinking in others. In that tension, volcanoes found their stages. Giant volcanoes erupted with a scale that modern eruptions can only hint at. The eruptions of the early Earth were not occasional tantrums, but regular continent-sculpting events. Vast plumes, rooted in deep mantle anomalies or in the energetic aftershocks of large impacts, delivered molten rock in volumes that dwarfed anything human history records. Entire provinces of basalt, the geological behemoths later scholars would call large igneous provinces, poured out in outbursts that could cover millions of square kilometers with sheet-like flows. These flood basalts did not build cones so much as lay the planet in layers of fresh oceanic crust, their outpourings welded landscapes into new topographies and, in places, obliterated older crustal fragments. To picture such an eruption is to think in the language of unstoppable movement. Melt rose from depth as seams in the planet's skin opened like valves. Where the lithosphere was thin or fractured, lava welled and spread in continuous sheets, a viscous tide that smoothed and scalded everything in its path. In other places, where volatile content and local geometry conspired, explosive eruptions hurled pyroclastic clouds that rose high into the dense steam and gas-thick atmosphere. Those clouds expanded into curtains of ash and glass that traveled thousands of kilometers, rain of microscopic beads that blanketed the world, coating nascent soils and shading the surface from sunlight. Between the two modes, effusive flood basalt and catastrophic Plinian blow, the landscape was continuously renewed. The mechanisms that produce these giant eruptions are geological, but their logic reads like drama. Deep mantle plumes, columns of anomalously hot, buoyant rock ascending from the greater depths, punched upward, weakening the overlying lithosphere. As pressure dropped during ascent, the peridotitic mantle partially melted, producing basaltic magma. The magma rose through fractures and sometimes accumulated in large chambers near the base of the crust. When the walls of those chambers failed, through buoyant overpressure, intrusive heating, or tectonic cracking, the accumulated melt erupted. In many cases, the volumes were so large that the eruptions were sustained for millions of years, a slow, relentless pouring that changed the chemistry of air and sea as surely as it changed the shape of land. Volcanoes were not monolithic in style. Shield-like provinces with extensive, low-angle flows built broad plateaus, stratovolcano-like edifices, where volatile-laden magmas interacted with thicker crust, created steep cones and explosive calderas. But the most consequential forms were the sheet flows and the vast fields of pyroclastic deposits that could alter climate on a planetary scale. The degassing that accompanied these outpourings was monumental. CO2, H2O, SO2, halogens, and a suite of other gases were liberated into an atmosphere already heavy with steam and reduced species. The immediate consequence was often a greenhouse push from added CO2, followed, paradoxically, by short-term cooling where sulfur aerosols reflected sunlight. The planet's climate was, in other words, at the mercy of pulses. Warming epochs stretched by cumulative greenhouse gases and abrupt chillings set off by stratospheric aerosols. Life and chemistry, if they were trying to find purchase, had to endure a planetary system of alternating impatience and lullaby. The geologic choreography was wider than single eruptions. Volcanism worked hand in glove with nascent tectonics. The cooling crust bowed and cracked. Areas of buoyant, silica-rich lithosphere collided and accreted into larger fragments. Other sections were pulled beneath their neighbors and recycled. The classic image of plate tectonics, plates sliding past, toward, and under one another, may have been immature in these earliest chapters. Yet the processes that would later stabilize into global plate dynamics were being tested in local theaters, proto-subduction episodes, transient continents colliding and suturing, and the emplacement of granitoid bodies through repeated melting and reworking. Where subduction-like motions existed, they dragged volatiles and heat downwards, recycling surface materials and feeding volcanic arcs at the surface. Where they did not, crustal growth proceeded through intrusions and underplating. The result was a patchwork planet, in places young and basaltic, in others more silicic and even continental in character, but everywhere unsettled. This instability had a remarkable consequence. The early geological record, and with it the possibility of remembering early events, remained thin and scattered. Giant eruptions could bury nascent sedimentary basins under kilometers of basalt. Caldera collapse could swallow and remelt the stratigraphy. Repeated thermal reworking obliterated isotopic signatures. The steadiness required for long-term memory, that is, for rocks to preserve a faithful ledger of atmospheric composition or chemical evolution, was, for much of the planet's early time, an exception. What little continuity survived did so in resistant pockets, isolated cratons, mineral grains that hardened and were protected, sediments that simply escaped the sweep of fire long enough to be buried and preserved. In that sense, volcanoes were not just architects of landscape, but also gatekeepers of history. They decided which chapters would be legible to future interpreters and which would be erased. There is a deep ambivalence to the volcanic role. On one hand, eruptions were cataclysms. They sterilized surface niches, vaporized pools of nascent chemistry, and reset local ecosystems in prebiotic experiments. A single large eruption could deposit an ash layer thick enough to alter atmospheric temperatures for decades. Or a flood basalt could change ocean chemistry by injecting vast quantities of iron and silicate dust. Yet, on the other hand, volcanoes were providers. They delivered the very metals and mineral surfaces that catalyzed complex chemical reactions, iron, nickel, molybdenum, and other transition metals that, when presented in hydrothermal plumes and vent chimneys, encouraged redox reactions and complex organic assembly. Volcanic soils, once weathered, are rich in elements that later sustained biological productivity. Volcanoes, in other words, both destroyed and enabled. They were the hand that alternately scraped clean and fertilized the stage. Hydrothermal systems deserve particular attention in this narrative. Where magma intruded near water-saturated crust, where hot rock met ancient seas, convection systems established themselves. Water, heated by subterranean heat, circulated through fractures, leaching minerals and emerging with a concentrated stew of reduced compounds. At the seafloor, these outflows built chimneys and mounds, precipitating sulfides and clays. In the warm chemical gradients around these vents, mineral surfaces provided scaffolds for molecules to gather, orient, and react. In an otherwise merciless world, these gradients were islands of persistence. They were small in space, but vast in chemical opportunity, places where energy flow was continuous, where catalytic surfaces were abundant, and where the interplay of heat and chemistry was controlled enough to foster complex sequences. Volcanoes, by delivering heat and metals, created these workshops. The scale of early eruptions also had atmospheric consequences that are instructive. Sulfate aerosols from explosive eruptions scatter sunlight efficiently. In the aftermath of particularly large events, average planetary temperatures can decline as radiation is reflected back to space. This short-term cooling, layered over longer-term greenhouse forcing from volcanic CO2, created oscillations in climate regimes, warm intervals, punctuated by transient cold snaps. Those swings influenced weathering rates, sea ice extents, and ocean circulation patterns, all factors that, across millions of years, shaped chemical equilibria and redox balances. Periods of aerosol-induced cooling could increase oxygen solubility in surface waters, temporarily changing the availability of electron acceptors and donors for abiotic chemical processes. In some, volcanoes were a leading driver of planetary variability. Another consequence of prolonged, voluminous volcanism was the formation of early mountain belts and the beginnings of erosion and sedimentary cycles. When large volcanic provinces and intrusive complexes cooled and exhumed, they were subject to the quirky arithmetic of erosion, where relief existed, weathering began to act. Even if vegetation was absent, physical and chemical weathering, bolstered by acidic rains from volcanic gases, ground rock into clastic sediments. Rivers born from persistent rain and snow in higher regions carried this detritus to basins, creating the layered records that would later be studied for clues to the planet's past. Paradoxically, the areas that volcanoes had baptized with fire could, once cooled and weathered, become some of the richest archives of later time. There is a philosophical texture to these contradictions. The planet's early geology is a pedagogy of paradox. The processes that are most violent often create the most lasting structures. Those that obliterate also build. From the standpoint of a later, temperate era, the memory of those giant eruptions is ambivalent. They are agents of both scarcity and abundance. They wiped away fragile chemistries, even as they spread catalysts and nutrient substrates across newly formed land. They ensured that any incipient experiment in chemical complexity had to be rugged, patient, and able to survive cycles of catastrophe and calm. Consider, finally, the question of trace preservation. If there were any hypothetical artifacts from extraordinarily early times, chemical fossils, mineralized patterns, or even, in speculative thought, human-like made objects from a vanished deep past, the record shows how unlikely their survival would be. The very processes that shape a habitable world are relentless editors. Giant eruptions bury, remelt, recycle. Hydrothermal circulation corrodes and transforms. Tectonic aggregation and rifting shred and weld. The geological palette is one of active erasure. The fragility of memory is thus a central lesson. Deep time is generous in producing possibility, but stingy in retaining its relics. As this chapter closes, the image that lingers is one of theatrical intensity. Volcanoes in the young Earth were not mere suppliers of scenery. They were the playwrights, directors, and stagehands of planetary evolution. In their molten breaths, continents were born and reborn, atmospheres were forged and refashioned, and the architecture of chemical possibility was repeatedly edited. The listener should feel two concurrent impressions: the overwhelming scale of these processes and the deep humility they impose. The planet at this stage was less a static canvas than a living workshop of transformation. Its eruptions were violent punctuation marks, yes, but they were also the long circling acts that allowed a once molten world to accrete a skin, to build mountains, to manufacture soils, and to create niches where chemistry, and perhaps later life, could, with patience, make a claim. In the narrative of Earth's deep time, giant volcanoes are both terror and provision. They rewrite landscapes and, by their rewriting, reveal the planet's capacity for reinvention. The fragile crust that began to cool and harden did so under a rain of fire, and yet from that rain emerged the basic scaffolding of continents, areas of persistent rock, basins that could hold water, and surfaces that, finally, learned to keep their stories. The next chapters will take those solid forms and test them again, in slow collisions, in the grinding of plates, in the long choreography that eventually yields stable continents and the slow accumulation of climate and life. For now, however, the planet listens to its volcanoes, and in that listening, it is learning to remember. What can a single speck of mineral tell the listener about a planet's earliest moods, its tantrums, its mercies, and the hesitant gestures that would, billions of years later, permit memory? The question is small and precise, and it is the hinge for the chapter that follows. It asks the listener to trust that the smallest things can be the most eloquent, to listen, not to the thunder of continents, but to the whisper lodged inside a crystal. When volcanoes bellowed across a young world, they did more than fling lava and ash. They sculpted the skin of the planet into a savage relief. Basaltic floods spread as sheet-like oceans of black glass, cooling into jagged plateaus scored by fracture and column. Explosive eruptions blasted pumice and ash into the murky heavens. When that particulate rain fell, it stitched the surface with a quilt of tough and welded glass. Lava flows built terraces and plateaus, their cooling edges spiking into irregular ridgelines. In the interstices, in the crevices and the newly made hollows, gases escaped. Steam and sulphurous plumes vented relentlessly, exhaling an atmosphere that was chemically aggressive and texturally abrasive. The result was a topography that read like a dossier of extremes: pumice fields, angular pyroclastic deposits, and networks of fissures gouged by flowing melt. The world's skin was rough in the literal sense. Its textures bore the fingerprints of eruptions. Those eruptions were also factories. Where molten rock met gas and where pressure fell away, crystals began to form. In the glow of cooling magma, minerals nucleated, grew, and sometimes, if fortune smiled, were freed from their molten cradle and preserved. The first mineral species that took ordered form did so under conditions that would be dismissed today as intolerable. Temperatures that exceeded 1,000 degrees, pressures shifting with each convulsion, and chemical cocktails of silica, iron, and volatile components combined to produce assemblages that would become the planet's primordial toolkit. To say first minerals is to highlight two different processes. Some minerals condensed directly from a vapor produced by the vast heat of impacts, the fleeting condensates of silicate vapor that cooled into glassy beads, metal spheroids, and unusual refractory phases. These are the spherules and microdroplets that rained back after giant collisions, the microscopic shards that record the ephemeral furnace of a planet's adolescence. Other minerals grew from slowly cooling pockets of melt, the crystals that formed as magma oceans convected and fractionated. In those pockets, olivine and pyroxene, the dense magnesium and iron-rich silicates that are the backbone of planetary mantles, were among the earliest, crystallizing quickly as temperatures declined. Plagioclase feldspars floated and formed scabs of primitive crust. Over time, as fractional crystallization progressed, pockets of silica-rich liquid could become concentrated enough to generate more unusual and resilient minerals, zircons among them. Zircon is a kind of stubbornness given mineral form. Chemically zirconium silicate, ZrSi04, it is hard, dense, and remarkably survivable. Where many minerals recrystallize, dissolve, or are erased under heat and strain, zircon preserves. Its robustness derives in part from its crystal structure and in part from its willingness to incorporate uranium into its lattice while rejecting lead. That propensity turns zircons into clocks. As uranium decays into lead over geological time, the ratio between parent and daughter isotopes becomes a measure of age. The uranium-lead clock is, for the deep-time storyteller, a nearly miraculous instrument. It lets a tiny grain speak the date of its crystallization with impressive precision. The most famous whispers come from zircons found in the sedimentary rocks of Western Australia, the Jack Hills. These grains, when measured, returned ages as ancient as about 4 billion years. That number is not merely a curiosity, it is a narrative elbow that pushes the listener's understanding. A zircon that formed 4.4 billion years ago crystallized in an environment that had to be, by some measure, cool enough and chemically differentiated enough to allow silica-rich melts to exist and then freeze. In practical terms, that implies two things at once. Pockets of continental-like crust had already formed, and liquid water, not merely steam, had interacted with the crustal environment early in the planet's history. The oxygen isotopes locked inside those zircons provide subtler testimony. Oxygen comes in isotopic varieties. The ratio of heavy to light oxygen, expressed as delta O18, alters when minerals interact with low-temperature waters at the planet's surface. Many of the ancient Jack Hill zircons show elevated oxygen isotope ratios consistent with having crystallized from melts that had assimilated material altered by surface water. This is the geological equivalent of mud on a shoe, a signature that the zircon's parent rock had been touched by rain or runoff. In other words, the presence of certain zircon chemistries implies more than a magma chamber. It suggests a conversation between crust and liquid water, weathering, sediment transport, re-melting, already happening in the Hadean world. Hafnium isotopes inside zircons add another line of evidence. Hafnium, like oxygen and uranium, can be used as a tracer of crustal evolution. The isotopic composition of hafnium in a zircon reveals whether its parent magma was derived directly from the mantle or whether it had reworked older crustal materials. Some Hadean zircons exhibit hafnium signatures that imply they grew from magmas already contaminated with reworked crust, indicating that primitive continental fragments had not only formed but been cycled and remelted. This is geology telling a time-stretched story of small continents forming, colliding, and being reconstituted. a rehearsal for the larger tectonic choreography that would dominate later eras. The implication is profound and disquieting in equal measure for anyone who imagines the Hadean as a uniform inferno. The evidence etched in zircon says the planet's adolescent wardrobe included pockets of quiescent crust weathered by water, then recycled into magma. It suggests that Earth's earliest narrative was not a single, unremitting headline of fire, but an anthology of local chapters, molten expanses alongside rock islands where rain had left chemical footprints. Those small islands of endurance matter because they are the kind of conditions where chemical experiments can persist. A pool that is repeatedly flushed and concentrated by tides and rainfall, adjacent to warm rock and mineral-rich hydrothermal seepage, is a much more fertile laboratory than an endless searing ocean of melt. The process by which a zircon reaches a researcher's hand is itself instructive about survival. Zircons crystallize in magmatic environments, then may be eroded and carried as detritus into sedimentary basins. There they can be buried, heated, compressed, melted, or incorporated into younger rocks. That some zircons survive billions of years of thermal recycling is a stroke of geological luck paired with mineralogical tenacity. When they are recovered, these grains are windows. Thin section analysis and isotope geochemistry can extract not just age, but the conditions of formation, temperature estimates from trace element partitioning, oxygen isotope ratios signaling surface interactions, and hafnium isotopes narrating crustal lineage. But zircons are not omniscient. They do not tell the whole story, rather, they set constraints. A 4.4 billion year zircon does not prove the oceans covered the globe. It proves that somewhere, sometime before that grain formed, conditions allowed the crust to cool, interact with water, and then be remelted into silica-rich magma. The balance of evidence still supports a Hadean of extremes, cataclysmic impacts, magma oceans, and violent volcanism, while opening the possibility of surprisingly temperate microenvironments. Beyond zircons, the first mineral record includes other relics that speak to extremes. Condensed vapor spherules from large impacts, etched glass beads, and microcrystalline iron-nickel particles record episodes of superheating and cooling. Pyrite and other sulfides, common in hydrothermal precipitates, suggest reducing conditions in subsea vents. Layered silicas, the precursors to later chert, can be deposited where hot fluids meet cooler seawater, and clay minerals emerge where rapid weathering of volcanic glass proceeds under acidic, hot rain. Each mineral class is an answer to a different environmental question, where heat met water, which precipitates appeared, where vapor condensed, which glassy beads fell, where weathering reigned, which clays accumulated. There is, too, a narrative of texture. Eruptive terrains create unevenness, and that unevenness becomes a canvas for mineralogical diversity. Valleys carved by flash floods, terraces built by successive lava flows, and hollows filled by impact basins became focal points for precipitation and sedimentation. Hydrothermal systems concentrated metals into veins and chimneys that later became mineral deposits. When rain persisted enough to weather basalt into clays, surfaces acquired new chemistries, sorptive clays that could concentrate organics, iron-rich sediments that set reducing gradients, roughness at the landscape scale, tectonic ridges, collapsed calderas, rocky lava fields, therefore translated into chemical heterogeneity at smaller scales. This heterogeneity is key to the hopeful part of the story. If the early Earth were chemically uniform, complexity would have little chance to cross thresholds. Heterogeneous landscapes supply niches, a volcanic glass pocket rich in catalytic metal, sitting beside a tide-flushed mudflat that concentrates organics under the monthly stresses of the moon, is a fertile juxtaposition. In deep time, repeated opportunities of this sort accumulate statistical leverage. The listener should imagine not one perfect cradle, but millions of tiny workshops, each auditioning different chemistries against heat, mineral surfaces, and cycles of wetting and drying. Zircons and their mineral companions thus become more than passive relics. They are the planet's marginalia. They mark corrections and reinterpretations, instances where Earth's rough skin preserved a sentence in its own story. Each measured isotope ratio, each trace element concentration is an annotation that allows a partial reconstruction. Magma, composition, interaction with surface water, crustal residence times, and the tempo of recycling. Together, these lines of evidence compress a long argument into a few durable sentences. The Hadean was both violent and sporadically hospitable, and the ingredients for later habitability were present earlier than once thought. There is a human feeling that accompanies this realization, a combination of humility and relief. Humility, because the evidence insists that deep time is messy, selective, and often cruel to its own archives. Relief, because the same geology that erases also occasionally preserves the exact kinds of records that let the listener bridge a chasm of billions of years. To hold a zircon under the metaphoric lens of isotope geochemistry is to touch a shard of planetary memory. The grain does not speak of life or of cities. It speaks in the older currency of heat and water, in the grammar of melt and reworking. Yet in that speech lies the crucial implication. The planet had already produced, in its earliest chapters, places that could have hosted longer-lived chemical experiments. This is where the narrative of the Earth's infancy folds back into the larger arc. Volcanoes erupted and roughened the surface, gases were vented, atmospheres were rewritten, and minerals, the listener can now analyze, were born in the flare-ups and quiet pockets alike. The first durable minerals, zircons chief among them, did not simply appear, they carried with them a record of interactions that cheat the notion of a uniformly hellish world. Their ages, their isotopes, and their trace elements together whisper of water-washed crustal fragments, of early continental-like domains, and of cycles of melting and renewal. They tell the listener that the Earth's early story was not a single violent breath, but a chorus of extremes and mercies, and that within those mercies were the first clues that the planet could, eventually, become a keeper of memory rather than merely a hewer of rock. In the end, the listener should take away two images. The first is tactile, a roughened planetary surface stitched from lava, ash, and impact glass, porous and pocked, hosting vent chimneys and shallow tidal flats. The second is intimate, a tiny zircon grain older than most of the solar system's remembered youth, whose internal clock ticks down a date and whose isotopes sing of water. Together, they compress a paradox. From the violence of eruptions and impacts arose not only destruction, but the durable substrates for a slow, patient chemistry. Those substrates would over eons be read and reread until, at last, they pointed toward the possibility of life. The mineral record, then, is the first archive of a planet learning to keep itself. It is a testimony that even amid the roughest textures, the possibility of gentleness was being written, grain by grain. What if the most persuasive proof of an ocean's existence arrives not as a shoreline or a fossilized shell, but as a speck of atom-thin logic tucked inside a crystal? That thought anchors the next turn of the narrative. Tiny mineral witnesses, aged beyond most memories, insist that liquid water was not a latecomer, but a presence whispering into Earth's earliest chapters. And yet, in the same breath, the planet confesses a paradox, that even while water dripped and pooled, the world remained forbidding, a stage inhospitable to the stable life that humans imagine. The two facts, water earlier than expected and life still impossible, form a tension that will carry the listener through this section. The oldest tangible testimony remains, those stubborn zircons. They do more than tell time, they record environmental hints. When examined with the chemical exactness of isotopes, many Hadean zircons show oxygen signatures that betray interaction with low-temperature waters. Oxygen isotopes are not gossip, they are the arithmetic of temperature and exchange. Heavy oxygen becomes more common in minerals that have equilibrated with liquid water at relatively cool temperatures. In several zircons older than 4 billion years, the proportion of heavy oxygen suggests that their host magmas had processed crustal material that had been altered by surface water. The implication is startling in its economy. Someplace at some time in the Hadean, rock had been weathered by water cool enough to induce that isotope shift. Liquid water was not merely transient steam folding into vapor. It had puddled, percolated, and, briefly, lingered long enough to leave chemical fingerprints. Those zircons are not solitary witnesses. Geochemistry offers other voices. Hydrogen isotope ratios in certain minerals and inclusions can hint at the source and history of water itself. The isotopic composition of hydrogen in some older mantle-derived minerals and in delivering meteorites implies that at least a portion of Earth's early water inventory could have come from volatile, rich bodies crossing the solar system's natal thresholds. Carbon isotopes preserved in some of the oldest rocks indicate fractionation patterns that, while ambiguous, are consistent with organic chemistry having been sampled, altered, and sometimes buried. And then there are the more controversial slides of geological interpretation, the Ishua supercrustal rocks, the Nuvuajituk greenstone belt, and other archaic assemblages that some researchers read as sedimentary layering, as quartz-rich bars, or as chemical precipitates deposited in the presence of liquid water. Each claim carries caveats of preservation and reworking. The Earth's early memory is a palimpsest, overwritten many times, but cumulatively the data lean toward a plausibility that water existed locally, perhaps episodically, far earlier than classical models once allowed. To feel the full weight of that possibility, the listener should imagine not a planet uniformly doused, but a patchwork. Impact basins catching sporadic rains, low-lying pockets where steam condensed more readily, shallow tidal flats beneath a young, closer moon, and hydrothermal basins where hot rock met cold water beneath transient crusts. These were small theaters of aqueous chemistry. They were not global oceans of the modern kind, but they sufficed to weather rocks at the margins. In those microscopic oases, silica could dissolve and later precipitate as layers of chert. Iron could remain soluble and reduced, form and be concentrated into banded iron formations in later eons. Clays could form from the alteration of volcanic glass. The presence of such minerals in ancient strata suggests that the machinery of erosion, transport, and deposition, the basics of sedimentary geology, was turning even in deep time. And yet the listener must not rush to anthropic comfort. Water's presence is not identical to habitability. The same evidence that points to early liquid water also carries disclaimers of extreme conditions. The chemistry recorded in early minerals argues repeatedly for an environment that was chemically and physically hostile to. Stable biochemistry is known today. The sea may have existed, but it was not the placid incubator of life one might imagine. It was an alien ocean in many respects. First, temperature. Where zircon oxygen isotopes suggest low temperature alteration, other proxies insist that much of the surface remains scalding. The planet's heat budget, bolstered by lingering accretional warmth, radiogenic decay, and frequent impacts, meant that many reservoirs of water were superheated, aggressively reactive, and spatially transient. Pools cooled beneath thin crusts of glass. Others boiled away after each large impact. In such a world, life of the sort that relies on stable aqueous matrices would struggle to form and then persist. Chemical systems require time to assemble complexity, repeated cycles, slow concentration, gentle catalysis. When cycles are instead violent resets, the opportunity for stepwise accumulation narrows. Second, redox in chemistry. The early atmosphere and ocean were reducing in character, abundant in hydrogen, methane, carbon monoxide, and iron in soluble, reduced forms. That redox landscape is both promising and threatening. It is promising because reducing conditions power reactivity. Hydrogen-rich environments support a host of organic syntheses and permit chemical pathways unavailable in oxidized settings. It is threatening because many building processes for robust, adaptable metabolisms demand stable niches with predictable electron acceptors and donors. In an ocean saturated with ferrous, iron, and sulfide, with oxygen either absent or immediately captured by abundant reductants, the energetic flows that biology later exploited were not yet organized into long-term, reliable cycles. Third, sterilizing energies. The young sun was more tempestuous in its ultraviolet output. The magnetosphere, nascent and variable, may not have fully protected surface environments from high-energy particles. Those photons and charged particles drive photochemistry, and, yes, they can produce organic precursors, but they also shred molecular assemblies. A world bathed in relentless UV would require any nascent chemistry to be sheltered beneath sediment, under mineral films, within deep hydrothermal conduits, or shaded by thick aerosols. Such refuges existed only sporadically and often were short-lived. The same lightning and ultraviolet radiation that fabricated amino acid precursors in atmospheric cauldrons would obliterate fragile polymers at the surface. Fourth, impacts. The continuous rain of extraterrestrial material, so central to the planet's acquisition of volatiles, also served as a persistent sterilizer. Each medium to large impact is a planetary-scale reset, vaporizing surface reservoirs, injecting heat, stirring the crust, and launching ejecta that can blanket wide regions with molten rock or glass. Even if life or proto-life had emerged in the most fortunate pocket, its survival depended on fortuity, being buried deep enough to be insulated, sequestered within subsea floor hydrothermal systems, or isolated in geologically protected niches. Those refugees were not many, and the odds against long-term persistence were high. Fifth, chemical toxicity and nutrient availability. The early seas were likely rich in dissolved metals and sulfides, but poor in accessible forms of phosphorus and fixed nitrogen, both essential for canonical biologies. High levels of iron and other transition metals can catalyze destructive reactions as well as constructive ones. Acidified rainfall in sulfur-laden atmospheres could weld mineral surfaces into forms that sequestered critical nutrients, making them unavailable to any emergent chemistry unless geological processes liberate them in. the right proportions. The balance between catalytic opportunity and toxic overload is delicate. Early Earth's chemistry frequently tipped toward the latter. This catalogue of constraints amounts to a stark conclusion. The mere existence of water, however early, did not equate to a hospitable cradle for life as it would later become. The conditions favored production of organic precursors and even episodic concentration mechanisms, but they also imposed an environmental lottery that made the stable continuity required for Darwinian-style evolution implausible. During much of the Hadean, the planet was still, in many regions, too hot, too irradiated, too chemically volatile, and too frequently reset. This does not eliminate the possibility of proto-biochemical activity. On the contrary, it reframes it. The early Earth becomes a laboratory of trial and abandonment. Hydrothermal vents, tidal flats experiencing rhythmic wetting and drying, mineral surfaces rich in catalytic metals, and microenvironments sheltered from radiation, these are the places where chemistry could iterate, fail, and occasionally succeed for brief intervals. Each successful assembly, however nascent, was likely local and ephemeral, a flicker in geological darkness. The process was noisy and stochastic, a million small additions rather than a single, deterministic genesis. The broader implication is philosophical and humbling. The presence of liquid water earlier than once thought expands the window for chemistry to do its iterative work. It makes the emergence of life possible on a planet that was still unpredictable. But it also insists on patience in interpreting such evidence. The existence of water is a necessary precondition for life, perhaps. It is not a sufficient one. Habitability is conditionality plus duration. Without long stretches of quiescence, periods that allow complex networks to persist, replicate, and be selected, chemistry might swing and sputter forever without achieving biological closure. There is, finally, a moral of scale that the listener should accept. The early Earth teaches that beginnings are messy and often cruelly patient. The tiny zircon grains and the isotopic whispers are not triumphant proofs that life surely once had an easy start. Rather, they are tokens of possibility amid adversity. They suggest that Earth hosted liquid water in isolated theaters and that within those theaters, chemistry rehearsed the preconditions for biology. Yet they also make clear that when the curtain rises on biology in the record, when the earliest unambiguous signs of life appear in the Archaean, the planet will have already navigated a long and violent adolescence. Life, when it finally stabilized, did so not because conditions were pristine, but because geologic patience, fleeting refugia, and a statistical abundance of experiments allowed an improbable continuity to be achieved. So the narrative tightens its focus. The Hadean's watery whispers are a double-edged testimony. They lengthen the potential rehearsal period and simultaneously emphasize how unforgiving rehearsal conditions were. For anyone tracing the arc from magma to memory, this is a sobering interlude. The evidence of early liquid water invites hope. The realization of inhospitable conditions tempers that hope with realism. The planet, in its youth, was generous in raw materials and brutal in preservation. That ambivalence is the crucible out of which everything that follows, including life, must be forged. The listener, now standing at this hinge, is asked to hold both impressions. The Earth's earliest waters may have fallen sooner than once imagined, but the world itself had not yet become a stable garden. Instead, it remained a theater of extremes, where chemistry could bloom briefly and be swept away. The eventual transition from fleeting experiments to sustained biochemistry required not only water and organics, but also a protracted period of environmental stability, a concession of time by a planet that, for much of its infancy, was not inclined to grant it. That concession, when it finally came, will be the subject of the next chapters. How episodic quiescence grew into ecological steadiness, and how the improbable became inevitable. What if disorder was not an enemy of beginnings, but their architect? That idea hangs like a small, sharp lens over the Hadean, a way of seeing the era not merely as an interval of destruction, but as a long, abrasive experiment in making complexity. The paradox at the heart of deep time is simple and unsettling. The same processes that tore nascent chemistries apart also concentrated, reworked, and recombined their ingredients into ever stranger assemblies. Chaos, in this telling, was not absence of order, but the engine by which new orders became possible. To follow that engine, one must shift from the comforting images of a single birthplace to a geography of repeated trials. The early Earth offered millions of laboratories at once, tidal flats alternately bathed and baked by a large, near-moon hydrothermal conduits pushing mineral-rich plumes into cold seawater, impact basins that filled, evaporated, and refilled as storms and meteor showers rehearsed their cycles. microscopic surfaces on dust and spherules where reactivity concentrated under the influence of lightning and ultraviolet light. Each of these niches hosted the same basic interplay: energy in, materials rearranged, moments of concentration where improbable chemistry could take its fragile steps. Energy is the primary currency here, and the Hadean was flush with it. Impacts deposited bursts of thermal and mechanical energy that compressed and heated matter into exotic phases, lightning-pierced. Cloud layers, dissociating stable molecules and creating reactive radicals, ultraviolet photons from a younger sun broke bonds, and pushed molecular assemblages into new trajectories. Hot rock met cold water and established steep gradients of temperature, pH, and redox potential. These gradients are crucial because chemistry does not proceed merely by having ingredients present. It proceeds when there is a direction for change, a bias that favors one reaction path over another. Gradients supply that bias. They create flows, electrons to be stolen, protons to be shifted, bonds to be assembled. In the Hadean, gradients were abundant precisely because the world was uneven and violent. Consider the tidal shore as a repeated experiment. With the moon closer and days shorter, shorelines with zones of intense mechanical and chemical cycling. Saline waters surged over wide, shallow flats, soaking into volcanic detritus and evaporating under heat. Each inundation dissolved organic precursors and mineral ions. Each drying episode concentrated those solutes, making polymer-forming reactions more probable. Clay-rich sediments and mineral surfaces bound and oriented molecules, promoting bond formation that would be improbable in a dilute ocean. The repeated rhythm, immersion, concentration, rearrangement, is the chemical analog of rehearsal. It did not guarantee a perfect product on the first attempt, but it provided repeated opportunities for chance assemblies to persist long enough to be tested by the next cycle. Hydrothermal systems offered a different, complementary theater. Deep beneath cooling crust, water percolated through hot rock, leaching metals and returning to the sea floor laden with reduced iron, sulfide, and other transition metals. At the point of exit, a continuous flow produced steep redox gradients. In minutes and hours, compositions that were stable at depth met oxidizing seawater and precipitated as mineral chimneys. Those mineral surfaces are catalytic, and in their porous interiors they create microcompartments, sheltered spaces where organic molecules can concentrate and where catalytic sites can facilitate polymerization. The idea of life beginning in vents is not merely romantic, it rests on the practical economy of continuous energy, abundant catalysts, and relative protection from irradiative sterilizers on the surface. Hydrothermal conduits are laboratories that run day and night on geothermal power, indifferent but reliable. Mineral surfaces more broadly deserve emphasis. Clays, metal sulfides, and iron oxyhydroxides are not inert backdrops. They interact chemically and physically with organics. Clays absorb and protect fragile molecules from hydrolysis and UV light. They can also orient monomers in patterns that favor chain extension. Iron, sulfur minerals act as electron mediators, enabling redox reactions that couple energy release to molecular assembly. In the prebiotic calculus, minerals act both as scaffolds and as catalysts, the first protoenzymes, not carved by evolution but emergent from the rules of inorganic chemistry. The fragmentary zircon record and the distribution of sulfide deposits in ancient terrains hint at the presence of such catalytic landscapes early in Earth's history. Those tiny mineral clocks and deposits are the geological residue of catalytic opportunity. The steady rain of meteoritic material, the cosmic grit that peppered the young world, added another dimension. Micrometeorites and larger impactors delivered not only water and volatile compounds, but also preformed organics, complex carbon molecules that had formed in interstellar and protoplanetary environments. When these organics fell into reactive settings, a sunlit puddle, an ash-laden tidal flat, a vent-adjacent basin, they mixed with freshly synthesized molecules from atmospheric photochemistry and lightning. The result was a heterogeneous soup, a chemical crowd in which novel pairings could occasionally produce longer chains and more robust assemblies. Delivery was episodic, so was preservation. Many organics were destroyed by heat, but some were shielded by sediment, trapped in microniches, or adsorbed onto mineral surfaces where they could avoid immediate annihilation. That last point returns the narrative to a crucial principle. Preservation of complexity requires pockets of quiescence within a sea of upheaval. The Hadean is best understood as a statistical environment. Most nascent assemblages were extinguished quickly, but given millions and millions of trials, rare events happen. A small set of molecules concentrated by evaporation on a sheltered shore and protected within clay interlayers could survive an impact because it lay beneath a layer of ash. A polymer formed in a vent might persist because it was continuously replenished by hydrothermal flow. Over deep time, the improbable becomes inevitable simply because the trials are so numerous. The chemistry within these pockets also began to develop selection-like dynamics. Molecules that were intrinsically more stable under local conditions, or that catalyzed their own production or the production of stabilizing partners, accumulated, or the catalytic networks, sets of reactions where the products accelerate their own formation, may have been favored. Molecules that adhered to mineral surfaces in ways that improved their replication likelihood were implicitly selected by the environment. The environment itself, with its oscillations of energy and concentration, acted as a sieve that favored stable, reproducing chemistries over ephemeral ones. In other words, before genes and proteins, the Hadean permitted selection on chemical systems. There was a pre-Darwinian selection where persistence, not reproduction as we define it biologically, was the criterion. Membrane formation and compartmentalization represent another critical step in moving from chemistry toward life. Amphiphilic molecules, those that possess both water-loving and water-avoiding parts, can spontaneously assemble into bilayers and vesicles in suitable conditions. Such compounds are plausible products of atmospheric and surface chemistry, and when present in shallow pools they form micelles and vesicles that encapsulate internal chemistries. Encapsulation confers two enormous advantages. First, it allows concentration of reactants. Reactions inside a vesicle can proceed at higher effective concentrations than in the dilute ocean. Second, it separates internal chemistry from external degradative influences, offering a protective microenvironment. Vesicles formed on mineral surfaces could also become tethered to catalytic structures, coupling compartmentalized chemistry to mineral-mediated reactions. These partnerships between membrane-bound compartments and mineral catalysts are among the most promising scenarios for achieving the first robust, semi-autonomous chemical systems. A related, often underappreciated mechanism is the role of wet-dry cycling in polymer formation. Many polymerization reactions that create long chains, nucleic acids or polypeptides, for example, are condensation reactions that release water. In a dilute, aqueous solution, equilibrium favors monomers rather than polymers. Repeated drying concentrates monomers and shifts equilibria toward polymerization. A subsequent rehydration can allow assembled polymers to be encapsulated or to interact with dissolved catalysts. The Hadean cycles, tidal, diurnal, and impact triggered, provided repeated wet-dry phases across vast spatial scales, testing polymerization under numerous chemical contexts. Where dry phases met catalytic mineral surfaces, the probability of producing longer oligomers increased. Electron flow is an essential ingredient for metabolism. In modern biology, it is organized by enzymes and membranes into pathways that extract usable energy from environmental redox gradients. In the Hadean, before enzymes existed, electron flow was mediated by mineral interfaces and simple inorganic catalysts. Iron-sulfur clusters, common in ancient hydrothermal systems and later central to contemporary biochemistry, could facilitate electron transfer between substrates. The so-called acetyl-like pathways postulated for early metabolism leverage simple chemistry, the reduction of CO2 using hydrogen and metal catalysts to produce acetyl-like molecules. Such pathways are plausible in vent environments where hydrogen is abundant and metals provide catalytic centers. In these contexts, the chemistry of metabolism could predate the complex molecular machines that later made it efficient. One must also consider the role of chance sequencing. The Hadean did not produce a linear series of improvements. It produced a branching, noisy tree of trials, most of which ended in dead ends. Yet some branches endured long enough for incremental improvements. Time was the silent ally. Geological patience, not human patience, but the planet's willingness to carry out millions of reactions. Cycles over hundreds of millions of years allowed the cumulative selection of chemical systems that could persist across perturbations. In practical terms, the early Earth was an audition stage running on a planetary schedule, an enormous number of left-field experiments, any one of which might have led to a persistent chemistry that eventually developed replication, heredity, and metabolism. This framing reconciles the earlier, sobering points. The Hadean was at once hostile and indispensable. High temperatures, ultraviolet fluxes, and frequent impacts posed severe constraints, but they also furnished the very conditions that make chemistry inventive: energy, gradients, and novel substrates. The mineralogical fingerprint left in zircons and in sulfide deposits is consistent with a world where both violence and shelter coexisted. Zircons tell of pockets of cooled crust touched by water, sulfides, and vent. Precipitates hint at localized. Reducing chemistries, impact spherules record episodes of superheating and subsequent cooling. The geological record is fragmentary, but its fragments point to a mosaic of niches. That mosaic is precisely what a complex chemistry needs. Diversity of environments to explore, not a single perfect cradle. There is an emotional contour to this scientific argument that matters for how it is received. The human listener, accustomed to narratives of tidy causality, may prefer a single origin story, an elegant locus where life began once and for all. The Hadean refuses that comfort. It offers instead the more challenging and more truthful image of a patient experimenter, indifferent and repetitive, that allowed many failures and a few rare continuities. This picture is not demoralizing, it is liberating. It expands the realm of possibility and explains how improbably complex outcomes, like life, can arise without miracles. Given enough trials, energy, and persistence, life becomes one of many statistically possible endings to a long and noisy story. From the vantage of these arguments emerges a clear transition. Chaos is not merely the stage of erasure, it is the workshop of invention. The alternating violence and repose of the Hadean repeatedly reset and reassembled chemical systems. But within that restlessness, small islands of stability accrued the memory necessary for biological continuity. The formation of membranes, the catalytic promise of minerals, the repetitive cycles of wetting and drying, the steady input of energy through heat and radiation, these are the components of a long, patient convergence. The final and most consequential lesson is about contingency. The particular sequence of impacts, the timing of the moon-forming collision, the retention of volatiles, the distribution of catalytic minerals, each is contingent. Had any been substantially different, the inventory of safe niches might have shifted, and the pace or even possibility of life could have changed. That contingency is not an indictment of chance, but an account of scale. The architecture that led to life is a complex, contingent construct built from innumerable accidents that together became favorable. The Hadean's chaos thus reads as the necessary preface to biology, a period of trial that, in aggregate, built the conditions for chemistry to edge toward persistent, self-propagating systems. As this section closes, the listener should feel two concurrent impressions. First, humility, the recognition that the origin of life, if it emerged in the Hadean, was the product of a gauntlet of destructive and creative processes, not a single felicitous event. Second, wonder at the way planetary-scale violence and microscopic chemical subtleties combined to produce environments where astonishing complexity could accumulate. The Hadean's chaos was not the enemy of life's possibility. It was the crucible in which possibility itself was annealed. The subsequent chapter will draw this chorus into a reflective close. It will ask, in quieter terms, what it means to call an era the beginning, to permit the Hadean to be both the furnace of erasure and the misty birthplace of biology's long arc. In that conclusion, the listener will be invited to hold the Hadean as both violent and merciful, an incandescent prologue whose very fog, dense, opaque, and abrasive, nonetheless allowed the first slow, improbable whispers of life to incubate. What if the storms and the shattering impacts that scarred the planet's earliest surfaces were not mere obstacles to life, but the very forces that made life possible? That question hangs like an ember at the end of the Hadean, small, bright, and dangerously provocative. It reframes the long adolescence of the Earth not as a preface of wasted fury, but as an experimental laboratory in which chaos and order were braided together. To close the story of the planet's first acts is to stand, for the last time in this series, at the threshold between two ideas, that life needed calm to begin, and that life might instead be the reward of disorder. The evidence assembled so far reads like a forensic sketch of persistence. Thea's collision rewrote day length and tides. The magma oceans churned and sorted the planet's interior. Volcanic provinces belched cataclysm and deliverance in the same breath, and the meteor rain both seeded and scoured. From the rubble and vapor, pockets of crust cooled, zircons preserved temperature and water fingerprints, hydrothermal vents stitched heat to chemistry. In every instance, destruction and provision arrived together. The narrative is cruelly consistent. The planet supplied raw ingredients by breaking things, and then some of those broken things became the scaffolding for slower, more delicate processes. There is a particular logic to that cruelty. systems far from equilibrium. The molten skin of the early Earth, the boiling plumes of hydrothermal vents, the charged columns of stormy atmospheres do not conserve simplicity. They channel energy through matter, and when the flow is strong, structures emerge that persist only because they can dissipate energy efficiently. That is the essential idea behind dissipative structures. An open system with throughput can maintain ordered patterns precisely because it consumes disorder. Lightning and ultraviolet light tore apart molecules at the surface, but those same forces created reactive fragments that could recombine on mineral surfaces. Tides, once violent, wrung salt and organics through shallow intertidal zones, alternately dissolving and concentrating. The atmosphere, thick with carbon monoxide and methane in early times, hosted dramatic photochemistry that produced a menagerie of organics. Meteorites delivered still more. Each violent act was at once an eraser and an author. To call this a recipe for life, however, is to oversimplify. There is a difference between producing organic molecules and building a persistent, self-propagating chemistry that can evolve. Hadean's inventory of energy and ingredients created the necessary ingredients for complexity. Amino acids, lipids, nucleobase precursors. But without sufficient temporal continuity, those molecules sputtered and vanished. Most experiments failed. The planet's early history reads as a vast statistical sampling process. Millions of microenvironments run in parallel, most of them short-lived, a few of them long enough to approximate continuity. Persistence, not miracle, was the scarcity at stake. Which microenvironments managed to persist long enough? The geological record offers hints. Hydrothermal systems delivered continuous energy and catalytic mineral surfaces. Tidal flats produced rhythmic concentration. Through wetting and drying, sheltered basins, once filled, provided pockets where radiation and direct impacts were mitigated. Zircon records whisper that somewhere the crust had cooled and been washed by liquid water, not globally, but patchily, and that those pockets were repeatedly reworked rather than erased. That repeated reworking matters. It meant that the same locale could be the site of numerous trials, depositions of organics from the atmosphere or meteoritic infall, catalytic encounters on mineral surfaces, cycles of concentration and dispersal. In an environment of persistent cycles and catalytic scaffolds, chance assemblages could move from ephemeral chemistry to reproducible systems. This is where the role of minerals cannot be overstated. Clay layers, iron-sulfur precipitates, and newly formed feldspar surfaces acted not only as passive substrates, but as active participants in chemistry. Clays absorb and orient monomers. Iron-sulfur phases mediate electron flow, glassy spherules, and metal. Beads supplied microlaboratories. Those surfaces sheltered molecules from ultraviolet assault, concentrated them, and sometimes presented reactive arrangements to privileged polymer formation. In short, the planet's inanimate parts did the work of proto-enzymes before life itself could invent biocatalysts. Yet contingency creeps in at every turn. The moon's birth stabilized obliquity and amplified tides. It changed the clockwork of the Earth. Had Thea's geometry been different, the tides might have been chaotic rather than rhythmic. Seasons might have swung wildly. The presence and retention of volatiles, water, carbon, nitrogen, depended on a delicate balance between delivery and loss, on the timing of impacts relative to cooling, on the magnetic field's ability to shield against solar stripping. Different initial conditions could have left a planet dry or choked under a runaway greenhouse, or bereft of useful catalytic metals at the surface. In other words, chaos produced the ingredients, but the specific sequence and geometry of chaotic events determined whether the recipe could be completed. This is the heart of the open question. Is life inevitable in worlds forged by turbulence? There are two competing intuitions. One is optimistic. Given enough time and enough non-equilibrium chemistry, self-organization is the natural response of matter. Energy fluxes produce gradients. Gradients allow directionality in reactions. Directionality enables networks that can sustain and expand themselves. In this frame, life is a thermodynamic consequence of a planet's drive to dissipate energy. The other intuition is soberingly less certain. The path from organics to autonomy traverses narrow thresholds that are sensitive to noise. Only certain sequences of events permit the continuity necessary for Darwinian evolution. Under this view, life is not inevitable but probable only under particular confluences of circumstance. Modern theory and experiment do not yet resolve the tension. Laboratory work shows that many building blocks of life can be created from plausible early Earth mixtures of gases and energy. Mineral catalyzed syntheses and wet-dry polymerizations can generate longer chains. Autocatalytic sets can, under controlled conditions, exhibit rudimentary reproduction. But these are demonstrations of possibility, not proofs of inevitability. They prove that the steps are not metaphysical miracles. They remain, however, contingent on spatial and temporal settings that the planet must furnish. In the empty expanses of deep time, possibility still requires carrying capacity. What complicates the question further is scale. Deep time is patient in a way human narratives are not. Where a single experiment in a laboratory fails, a planet repeats a million similar trials over hundreds of millions of years. That repetition is an amplifying factor in favor of emergent complexity. Even extremely improbable transitions become almost certain if the number of trials in the temporal window are large enough. In that statistical sense, the Earth's long, violent toddlerhood could be read not as an obstacle but as a generous lottery. So many draws that improbable winners are almost guaranteed to occur somewhere, sometime. But there is a counterweight, selection by catastrophe. The sane processes that let experimentation occur also winnow the field. Giant impacts and global remelting reset the chemical page. Volcanoes deliver catalytic metals but also acidify and sterilize. Solar UV crafts organics and destroys them. The point here is subtle. The Hadean chaos both increases the sample space and reduces the survival probability of any given nascent system. The balance between generation and attrition shapes the net likelihood of a self-sustaining chemistry emerging. If generation vastly outpaces attrition in the right niches, then emergence becomes probable. If attrition is too frequent or too thorough, then generation remains academic. One of the lessons embedded in the mineral record is that the Earth found a middle way. It did not tame chaos immediately, nor did it surrender entirely. Instead, through a sequence of partial stabilizations, the formation of a magnetic shield, the gradual decline in impact frequency, the emergence of durable crust, the planet increased the frequency and size of niches where persistence could occur. Those gradual changes mattered more than any single event. They tilted the odds by offering longer windows in which chemical systems could mature. Life, if it arose, did so not in a single lucky instant, but in the cumulative softening of adversity. That cumulative softening is also what grants the Earth a moral weight in the present. If life is a product of deep, contingent worldly processes, then the continuity of those processes becomes fragile heritage. The tangled history that enabled biology, a magnetic core that grew stable, oceans that were retained, climate feedbacks that eased extremes is not inevitable in cosmic terms. It is a set of conditions that future generations of whatever sort inherit and can still influence. Recognizing the role of catastrophe in life's emergence should not breed fatalism, it should bring humility. The planet's ancient patience is finite in the face of new perturbations. Understanding the interplay between chaos and life is a call to stewardship, to preserve the fragile set of processes that allowed a long, improbable experiment to succeed. And yet the final thought must be a question, left open and resonant. The idea that life might be the inevitable fruit of turbulent planetary adolescence is comfortingly democratic. It would mean that, given enough time and disorder, the cosmos seeds life widely. The opposing possibility is no less profound, that life is a rare confluence, an outcome of particular angles and timings. Both views insist on a deep humility before the cosmos. Either life is an expected outcome of physics writ large, or it is a precious anomaly whose rarity should spur wonder and care. Here, finally, is the last image that lingers, not a newborn world neatly cradled into habitability, but an Earth that learned, through a chorus of storms and impacts, to convert violence into opportunity. The planet did not change by relinquishing its character, it changed by accumulating those moments of balance amid chaos. Storms carved niches, impacts redistributed ingredients, volcanoes provided catalysts, and tiny, stubborn crystals preserved evidence of fleeting calm. From this entanglement of force and tenderness, from the roar and the hush, life would, if it did, learn to read its first lines. Whether that learning was inevitable or improbable is a question that sits as both challenge and invitation. It invites science to continue, to look for signatures elsewhere, to test models, and to keep refining probabilities. It invites listeners to hold wonder and restraint in equal measure. In the end, the Hadean's lesson is neither nihilistic nor triumphalist. It is a meditation on method. That large-scale ruin and small-scale preservation can be partners in making something new. That chaos is not only a destroyer but also a sculptor, and that patience, geological patience, is the substrate on which life's improbable persistence rests. The storms and the battering impacts were, paradoxically, also the midwives of a world that could one day ask itself why it remembers. The open question remains, is the deliberate choreography of disorder a universal path to life, or is Earth a rare composition that cannot be easily replicated? The answer still eludes the instruments of observation and the equations of theory. For now, the planet continues on, a long-time learner that carries in its rocks the memory of its own bruised adolescence and the hint that, amid the storms, possibility found a voice.